今何も共有されてまでないですね。
あ、これだと全然ダメなんだな。
なんかそろそろライブ配信されてるかもしれないですね、これ。い
ああ、そうですか。あ、じゃあそろ
や、
そろやっ
大丈夫です。まだ大丈夫だと思うんですけど。で、これでフルスクリーンモードにすると、
スクリーンにすると、やっぱり発表しちゃうの。
いや、なりました。
なりました？
今フルスクリーンになってます。
あ、
なぜ
そう、
かわからない。
よかった。これでいきましょう。
はい。
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 Thank you very
はい。は
much.
い。よろしくお願いします。
はい。雨が降ってきた。
Good morning, Dr. Yukari ma'am.
Good morning.
Good morning. Yeah, I got your PDF file. Yeah.
Yes.
Can I see where is the Professor Dev Niyogi sir? He is there?
I don't see his name yet. I don't see Professor Niyogi yet.
Yeah. I also don't find because yeah, there is no communication from him. So people are joining very fast. So let us wait for 2-3 minutes.
Okay. In case Professor Niyogi doesn't come in 1 minute, shall we switch the speaker?
Wait for 1 more minute, otherwise we'll start from second speaker.
Yeah.
Okay, second speaker is myself.
Yeah.
Okay.
Patnaik, just now I contacted Professor Dev Niyogi, and he's having some trouble, so I've sent him the link again to his email.
Okay, I'm just sending. Can I
Okay.
put in the chat box also? No, so he not able to join. Okay, I'm sending, sir.
Yeah, I have sent him. You can also send him just.
Okay, sir.
Hello? Yeah, I'll wait. Okay, I've sent it both to your Gmail and WebEx.
Hall A, I have also sent.
Oh, it's connecting? Yeah.
In email to Dr. Niyogi now, right now.
Don't worry about it. You sell Dave Niyogi and then you join it. You just click join. It will work. Email is coming, right? Email is coming. Email and then join. Just right. Should I ask them to go with the next speaker and then we come back to you?
Yeah, I've joined.
Okay, then Dr. Patanaik, shall we start with the second speaker?
Yeah.
Okay, so we can start it.
Yeah.
And we can swap when Dr. Niyogi joined, we can have it his talk.
Okay, so let us switch the order.
Yeah. So, so very good morning, good afternoon, good evening to all our viewers for the last day of our IWM-7. And now we'll start the invited session. So now may I request Professor Yukari and Takayabu to kindly chair the session. So yeah, Dr. Yukari obtained MSc degree in 1985 and PhD in 1993 from the University of Tokyo, Japan. The topic of her PhD was Organized Cumulus Convective Systems over the Tropical Pacific Ocean. Dr. Yukari research topics are primarily in tropical meteorology, tropical convection, and global climate, global precipitation. She has received many awards such as 1998, the Japan Meteorological Society Award, 2017, Soroshi Award, Distinguished Women Scientist Award, 2021, American Meteorological Society Fellow. Professor, yes, from 2019 to present, the Vice Director, Atmosphere and Ocean Research Institute, the University of Tokyo. Earlier, she was the member of the Scientific Council of Japan, professor in the Tokyo University, associate professor, and so on. So over to you, ma'am, now to kindly chair the session.
Thank you very much for nice introduction. Okay, thank you very much for gathering to this session. The session, because I will chair the session, and because the first speaker, Dr. Niyogi, is Dr. Niyogi here? Not yet. So we will change the order and start with the second speaker. Like actually, the second speaker is myself. So let us start. Can you see the screen?
Yeah, we can say full screen, make it full screen.
Is it in full screen?
Yeah, it is full screen.
Madam, please.
Okay.
It's not in the full screen. Now the screen is split into two. So can you go back?
Can
please exit from the full screen now.
Is it in full screen?
No, madam. I will guide you how.
Do you see two screens?
Yeah, two screens we are seeing.
I see. How about this?
No, not still.
One more
Not
time.
yet. Okay. Okay. Sorry for the
Yeah, now it is okay.
Oh, okay.
Okay. Okay, I will do it with this
Again,
one.
it is down. Oh, yeah, now it's fine.
Okay. So the title of my talk is Warm Season Heavy Precipitation Observed from Satellite Earth Observation. Thank you very much for this opportunity to present our recent works. Today's my talk is based on studies with Hiroki Tsuji, Chie Yokoyama, and Atsushi Hamada. I'd like to acknowledge my collaborators. Oh, it doesn't go. Okay. In recent years, frequency of wide area heavy rainfalls causing disastrous floods is increasing in Japan. This photo of Mabicho in Kurashiki is taken at the July 2018 heavy rainfall event. Over 237 lives were lost from this flood. After this event, we have been continuously suffering from record-breaking heavy rainfall events in 2019, 20, and also last year. Recently, we can utilize ample amount of accumulated spaceborne radar data from TRMM and GPM. This movie by JAXA shows a snapshot of a typhoon captured by the GPM DPR. By capturing rainfall events in 3 dimensions, we can investigate characteristics of rainfalls with their height, area, stratiform convective ratio, and so on. Utilizing 11 years of TRMM PR observation data, we made statistics of top 0.1% extreme rainfall events and extreme convection events at each 2.5 by 2.5 degrees latitude and longitude grid. Extreme rainfall events are defined with maximum near-surface rainfall, and extreme convection is defined with maximum height of 40 dBc reflectivity. The left panels show 3-dimensional histograms of precipitation pixels over land for 30 degrees north to 30 degrees south. We can see that rainfall extremes are not very tall, while convection extremes are not extremely intense at the surface. So it is found that heaviest rainfall is not often accompanying tallest convection. I found in Dr. Yali Luo's talk on Wednesday, it is consistent with the observational evidence recently. Okay. Son et al. 2013 had compared heavy rainfalls over Korea and over Oklahoma. They showed that in the moist Korean warm season, the extreme rainfalls consist of warm type rainfalls, while in Oklahoma, they are mostly cold type rainfall. Our results are very consistent with their warm types and cold types. And in the right panels, Hamada Takayabu further compared the rainfall extremes and height extremes around Western Japan, this region. We found that rainfall extreme systems have larger size and larger stratiform ratio, relatively low convection, and less lightnings, indicating they consist of well-organized mesoscale systems. The environments for their environments are relatively more stable compared to the climatology, but very moist in the lower troposphere. Then what causes heavy rainfalls? Conventionally, CAPE is often used to measure the instability for heavy rainfalls. It is in any textbooks. And it is effective to measure the potential for very tall thunderstorms under the condition with warm air below and cold air aloft. However, another essential instability with very moist atmosphere has not been equally considered. It is the most absolute unstable layer called mole, as introduced in Brian Fritsch. When the atmosphere is very moist, even the cap is not very large, a layer lifting causes a kind of absolute instability to trigger convection, and moreover, can be maintained by continuous free tropospheric moisture supply. This kind of instability is associated with mesoscale convective systems and can cause wide area heavy rainfalls. This panel shows the three-dimensional rainfall structure captured at around on July 7, 2018 heavy rainfall case. I showed the photograph in the beginning. It is clearly seen that despite the record-breaking rainfall amount, rainfall height, you can compare with the scale here, rainfall height over 10 kilometers is scarcely observed. Now, left panel shows Himawari 8 water vapor image. Here's Korean Peninsula, and here's Japan under the thick clouds. And the right panels show potential vorticity at 350 Kelvin in black contours, and rainfall in color shades and precipitable water in red contours. A band of very heavy rainfall appears in front of a deep upper level trough here. And it is analyzed that this trough dynamically prepared the updraft with very moist atmosphere in its front and caused the persistent heavy rainfall. And it is reported that the July 2018 event is scarcely accompanied by lightnings. Here, we compared this event with the previous year's heavy rainfall when the active lightnings were reported. These are 24 hours accumulated rainfall for both events. We can see that 18 case, there's a much wider area coverage, while that 17 case is confined to northern Kyushu. We then compared the time series of JMA's northern Kyushu ground-based radar data for these cases. Red curves are for numbers of very tall rain grids with ecotop height larger than 10 kilometers, while blue curves are for rain grids with moderate height rain grids with ecotop height less than 10 kilometers. We can readily see a distinct contrast between the two cases. For the 18 case, rainfall amount is primarily from moderate height rainfalls, while in the 17 case, heaviest rainfall is brought by the tall rainfall over with ecotop height over 10 kilometers. It is consistent with the difference in lightning activities. These panels compare environments in anomalies from the climatology. Left panel shows temperature anomalies, and right panel shows the moisture specific humidity anomalies from the climatology. The blue curve is 2018 case, and the red curves are for 2017 case. We can notice that temperature stratification in 18 case is even more stable compared to climatology, while it is more unstable in 17 case. For the moisture specific humidity, both cases are very humid, but extremely humid in 18 case. So this contrast well corresponds to the statistics for extreme rainfalls and extreme convection I showed you before. At last, we compared the vertical cross sections. The left panel shows the plan views for the radar and Himawari clouds. We further diagnosed the mold condition for 2018 case. And at this white dashed line, we made vertical cross sections for the color shades shows horizontal wind speeds and vectors are wind vectors. And the black open O's you can find shows the grid. The mold condition is satisfied. Okay. And we can find, comparing with the schematic by Brian Fritsch here, we can find a very similar condition with deep inflow layer lifting, preparing the mold condition, and maintain the continuous heavy rainfall in this area. Let's go. Come on. Okay. To summarize the comparison results, for the 18 case, a long-lasting rainfall occurred over an extensive area from moderately tall precipitation systems. Compared to the climatology, atmosphere was more stable but extremely moist. The upper tropospheric trough played a role to dynamically induce the ascending motion, which provided such environment for a widespread heavy rainfall. For the 2017 event, short-term rainfall occurred in a narrow area from extremely tall precipitation systems. Atmosphere was more unstable compared with the climatology. The upper trough played a role to destabilize the atmosphere, which provided environments for a very tall convection with lightnings. Lastly, a statistical study was performed. 62 heavy rainfall cases with Kyushu region surrounded by this red rectangle mean Kyushu region average rainfall over 60 millimeter per day are selected from 15 years warm seasons. Left panel shows composite time series relative to the regional mean rainfall peaks. Rainfall peak here. And purple is precipitation, and blue shows free tropospheric moisture convergence, and red curve shows the boundary layer moisture convergence below 1 kilometer. we can notice that free tropospheric moisture convergence well precedes the rainfall increase, even 24 hours before the precipitation peak. Right panel shows the grid numbers in the same region where mole conditions are diagnosed. We can confirm that mole is associated with very heavy rainfall cases. Free tropospheric moisture convergence prepare mole condition with deep layer lifting, which maintains the heavy rainfalls. To summarize, in recent years, frequency of wide area heavy rainfalls causing disastrous floods are increasing in Japan. And statistical studies of rainfall events observed from spaceborne precipitation radars revealed that extremely heavy rainfalls do not often accompany extreme tall convection. Environments for heavy rainfalls show relatively stable but extremely moist condition. There are two types of heavy rainfalls. One is with Cape-type instability. Another is with moist absolute stable layer. Wide area heavy rainfalls are associated with free tropospheric moisture convergence, preparing mole environments, which is favorable for organized convection. Atmospheric water vapor amount has been significantly increasing in past 30 years with the global warming. We should prepare for a further increase of mole-type heavy rainfalls in the warmer climate. Thank you very much. And okay, the talk is open for questions. Sorry, because I am opening my summary. I cannot see the your hands. So could you speak up if you
Hello?
can? You have a
Hello, can you hear me? This is
yeah, I can hear.
yeah, thank you, Dr. Yukari Takayabu-san. Very nice talk, excellent talk.
Thank you.
I have just one question. You compared the July 2017 and July 2018, and
Yes.
18 heavy rainfall, you showed it is more dynamically induced, heavy precipitation. And the 17 was more of a Cape type of instability. So my question is, the July 2017, was it also related to a typhoon or something? Was it due to typhoon 2017?
2017 case was not with the typhoon case, but it is associated with, I didn't show for the 17 case, but it is associated with also a trough it was coming.
Yeah.
Atop of this region here, but shorter trough and with and just below the trough cold air, this heavy precipitation happened.
Okay. Yeah.
Okay, and this is also this case is also associated with the deep trough and associated with the uplift of the whole thing, but the rainfall itself is not associated with the large scale uplift, updraft, but it is also the organized system.
Okay, but the 18 was associated with the typhoon activity, was it?
18, yes, there was a typhoon just before this thing. So typhoon prepared, typhoon in remote place already prepared the very moist condition. Also prepared the moist atmosphere. It was also important.
Thank you very much, Kari-san.
Thank you very much. So if there's no other questions, it's just on time. So let me stop my screen. Just a moment. 共有を停止. Okay. So we are back to this screen. And do we have Professor Niyogi?
Yes, he's available.
Thank you very much. I'm glad to see you. So thank you very much. I would like to introduce Professor Niyogi. Just a moment. Okay. Dr. Dave Niyogi is John E. Brick Elliott Centennial Endowed Professor at the University of Texas at Austin in the Jackson School of Geosciences and Department of Civil, Architectural, and Environmental Engineering. He is a graduate faculty at Alden Institute of Computational Engineering and Science and University of Texas Center for Space Research. He is also Professor Emeritus, Purdue University, Department of Agronomy and Department of Earth, Atmospheric and Planetary Sciences, and former Indiana State climatologist. And Professor Niyogi's research seeks to significantly contribute to our understanding of the Earth system, particularly the urban and agricultural landscapes, and the dynamic role of coupled land surface processes on weather and regional meteorological extremes. An important, ongoing, and emerging focus of his research is to translate the scientific work undertaken into decision tools and portals with a particular focus on hydroclimatology and sustainable climate-ready resilient cities. Thank you very much for attending to this workshop. And let us start your talk. So
very much. Thank you very much, Professor Yukari Takayabu, as well as all the dignitaries here at the IWM-7. It's really a pleasure. I wish things would have been improved just a bit, that I could have been there in person, but this is the best I could do to at least get a chance to interact with all of you. Considering we have about 15 minutes available for this talk, I'll try to rush through. There are several things that I'm wanting to share, and I hope in my excitement, if I am exceeding my time, that the chair will guide me to stop, and I'll be happy to pause at that moment. So without much ado, let me say that what I'm going to be talking about is essentially the role of land surface feedbacks, particularly from the context of the Earth system models. I'm going to be focusing more on the context of trying to make a case for the human-dominated landscapes, the emerging role of AIML, digital twins, and sensing the unsensed is going to be towards the end of my talk about what and some of the comments related to that, especially as we go into the context of land surface processes. This presentation is, when I look back at conferences, one of the things I always remember is that during my PhD and earlier days, these were influential. The experts who are here, there is nothing much I can tell them. I'm here to learn from them, but perhaps there are some emerging researchers and some PhD scholars who are trying to look for some topical areas, and this particular talk is really targeted towards them. The point I want to raise in my talk is that monsoon research is one of the most important and timely topical areas in the world right now. And there are obvious reasons for this. There's the concentration of population, the economic burst that is going on, the preponderance of hazards, and the highly vulnerable communities that all exist in and around the monsoon belt region. So even when you say, I want to study climate, even do you study, I want to study any of the topical regions, monsoon research is really the confluence of everything that the humanity can do right now. And I really challenge all the aspiring researchers to continue that research domain going forward. The second point I will really make is that in the context of monsoon, I'm going to highlight the role of land scale feedbacks and how high resolution information is starting to become extremely critical. We are no longer interested in just knowing what is happening at a continental scale, but really what is happening at a finer and finer scale. And with that, the role of boundary layer and land surface processes are starting to grow. For those of you who would like to read some more about the improvements that are going on, I recommend this really interesting book that came up in a similar such workshop a couple of years back, in 2019 actually, that has been published. Dave Randall, J.S. Ravi Mukhopadhyay, and several others that were involved in that. It talks about the physical processes. In particular, there's one chapter I have which is related to land surface processes, and anyone wanting more details, I would say please read more along that chapter going forward. And indeed, when you're talking about monsoon, you must have heard about a number of fantastic talks, but I would also highlight continually that look into some of the reviews, the seminal work that has gone on in prior studies. One that I use quite routinely is the work by Professor Gargill in my class, and also the papers by Peter Webster and his recent book and so forth. So the initial work, when we start looking into the context of the monsoons, has been on the large scale flow patterns and how the circulation patterns have evolved. There have been then a shift in terms of the manner in which the oceanic processes associated with variability and the active break phase has started to come up. And then there has been a series of papers that have been on the regional dynamics, work done by Krishnamurthy and Sikka and so forth. And here's a note I want to say to the students that I've started to notice, that let's not be lazy and just do a Google Scholar and then find what has been important in the last 5 years. Go back to the really 30, 40, 50 years before what papers have been published on this topic, and you'll find some really amazing knowledge that is not gleaned by just looking at one Google Scholar kind of survey going forward. The key point is that monsoon is not a monolithic singular event. It is not a single system that just gets dumped over a region. There are many features associated with it: onset, active break periods, depressions, onset that coming up and going forward, disturbances, cyclones, heavy rain events, and tremendous variability in terms of these spatiotemporal patterns that exist across the region. So monsoon, when you start thinking, is all of these things interactively working forward and moving. You can also look at it in the context of monsoons in terms of the applications that are emerging. That monsoon, from the context of what is required for, say, the agricultural management, where the timeliness, the spatial resolution, the events become important. From urban flood and flood management perspective, where you're looking at the quantum of the rains, the timing of the rain, and so forth. You're also looking at it from the context of what's happening with regards to the air quality in the region, especially in the monsoon region, as we call. And then, of course, we are in an energy pricey region, and so the wind energy and the potential that comes up. So each of these applications are now demanding more of us as we start saying that we are doing work in the area of monsoon applications. So there is a higher demand for more local scale, higher resolution information. There's a higher demand for all that things that we now feel are making a come of age for the boundary layer, local feedbacks, convection, and land feedback starting to come together. The era is emerging, the era is now. And in fact, like many of the things that Professor T. N. Krishnamurthy and Professor Sikka had been doing, and this is one of my prized paper, which was with both of these stalwarts, it essentially showed a key point. Even in their work, they said that when you are looking at the passage of the rain and the onset after making landfall, or when the onset occurs, that the first 20, 25 days, there's going to be a tremendous sensitivity to things like soil moisture and some of the land surface feedbacks coming forward. Unfortunately, this work has not evolved much. I mean, I know Arvindam and others have done some of the areas and some work in this area, but this is an area I think that is ripe for improved predictability going forward. There's a couplet I have put together in that book where it says that if you look at the land basked in the sun's rotation, and this is basically like a yogi balancing the energies, the moist, latent, potent, sensible, and the ground. And amidst these energies, you're going to get the turbulence and the thermals that are going to rise. And then you have this flux gradients, and then you're going to have convergences. And therein lies the whole process of convection and the rain that starts coming up. But when we are looking at this whole interplay that is going on, very often we have been focusing on clouds and the large scale dynamics without really understanding what has been the feedback associated with the land and the gradients and some of the heterogeneities and how they have triggered some of the vagaries that we call about in terms of the monsoon predictions going forward. So why does this happen? It happens typically because of many things that are going on in the monsoon domain. Deforestation, urbanization, irrigation, agricultural intensification, which all leads to changes in the energy balance, the feedback, as I mentioned in the previous couplet, and it has an impact onto the larger scale processes going forward. So there is a shift in time when we are looking at it in the context of the climatic shift about how the rural urban population has been shifting in this region, how the population intensity has been increasing in this region. And we have also been seeing tremendous agricultural and human domination of agriculture and urbanization. So if you look at it in the context of the monsoon domain, the human dominated landscapes, urban and agriculture, and the decisions that are coming up from the human perspective are dramatic. And if you look at what are the global land atmosphere coupling hotspots, they all align in places where there has been a human intervention into the atmospheric and water cycle going forward. And the monsoon region is one of that hotspot where we have to look at it. And we have an impact when we start improving land surface processes. As part of the National Monsoon Mission, we had created the first 4-kilometer, 30-year soil moisture, soil temperature data set. Now through NCMR, we have a even better, newer IDAA, the IMD data analysis that is available now. And under this, now you have information that is suitable in the context of providing information for the models. And under that, you can see an improvement associated with the land, associated with the feedback into not just local scale storms, but as you show here, in things like the monsoon depressions, in the simulation of cyclones and so forth. Here's an example about a thunderstorm simulation when you have an improved landscape and land surface presentation, that how it can improve processes at a micro scale, at a large scale, and how that could have an impact going forward in the context in which we try to represent the feedbacks associated with monsoon. But monsoon is not just the rain, it is all the interplay that goes on with it. And this is detectable. At the very simplest level, if you look at it in the context of urban heat island, in the context of how cities are creating changes in temperatures, it has an impact in the manner in which the heat waves start emerging. We have seen that in the 2015 Delhi heat wave, how the role of urbanization exacerbated what was happening with a large-scale heat wave, creating these pockets of highly potent heat regimes. We have also seen that in the context of future climate mapping, that how do we design cities? Are we going to have monsoonal systems which are going to be settling in, which are going to be spreading out? And they will have a dramatic impact in the manner in which the cities grow, compact, spread out, and the feedbacks would be quite different. And we know that the heating of the cities changes the domain of the urban domain, it changes the convergence patterns, it changes the rainfall, and the associated rainfall creates pockets of heavy rain. This we know by now. This is not something we are exploring. This is a known fact. And under that, we start seeing that even in the monsoon region, places where we have more urbanization, we have more increased rainfall occurring in our climatic data set. And this is something that has been noted now in a number of studies. Subimal Ghosh and others have, for instance, been doing a number of interesting studies around this topic. And we have been following up with this kind of feedback with global data sets in terms of analysis. Excuse me. So how do we represent these cities or agricultural effects, which are tiny micro scale features, into a large climate grid? How do you set this up into the scale with regards to what's happening with the monsoonal domain? How do you get this local scale forcing that could have a feedback that we want to represent in the model system? That is the challenge we are dealing with at this point. So what we need are requirements of an input, which are very difficult to come at a global scale. We're talking about human decisions. We're talking about data sets. We are talking about a community that needs to work together. So for instance, from the urban context, we have the International Association of Urban Climatology, IAUC, and we have created this World Urban data analysis and portal tool, the Wood app, which is providing the framework for studying what is happening with regards to the urban processes. But you can't just create data and the maps. You need to create the interface that goes from the data to the model and this parameterization. And that process is still missing right now. And so one of the way this is being done is what is being known as the digital twin of approaches for the Earth system models. Excuse me. So we have this proof of concept going on right now through a pretty large US Department of Energy project in which we are working with the Pacific Northwest National Lab, taking the E3SM model. We are putting the WRF model and the AdCirc, which is a storm surge ocean circulation model. And we are going basically across from 100-kilometer grids to 1 meter hydraulic inundation studies. And so the context is, how do you now take models which are at this multiple scales and try to have this scalability across very small to very big scales resolution? And there, of course, the approach seems to be that physical parameterizations, physical coupling, dynamical coupling will fail. That is not going to help. But this is where approaches like the AI, artificial intelligence, machine learning has been helping us create surrogate models and talk to each other and create this framework of scalability. And that looks very promising as we start looking at it in the context of the monsoon research going forward. Manmeet Singh, who is with Dr. Krishnan, he was visiting us as part of the Kalam Fellowship last year. And he helped us in do some of this work with regards to, the integration of the machine learning based cuboid sphere analysis and testing it out and so forth. And we have a couple of other students who are working in trying to create this digital twin framework. One such example of where we are trying to now put urbanizations or cities or agriculture into monsoon models or monsoon simulations for climate models is through this World Urban Data Analysis Portal tool, as I mentioned. And with that, we are not just getting now the maps, but we have started creating the framework for the vertical height of the buildings and other information, the kind of stuff that was not available before. This, by the way, is for the city of Bangalore. We had a project with Professor Mujumdar there from ISC on urban flooding, and we had been using this information for studying some of the urban flood aspects going forward. But here's the output from the Globus Data Set that has just been recently created by one of my PhD students, Harsh Kamath, who incidentally was at ISC with Professor JS for a while. And he has been working with a few of researchers here in terms of creating the satellite data sets and creating this a machine learning based approach for creating a high resolution urban data set for height. And that building height data, the Globus data set, is now we are trying to be integrating for the urban modeling studies in a global context. So the question now is no longer how to detect effects of land surface on monsoon systems, but really looking forward, it is how do we represent these effects? How do we take what we know about how land is affecting and start putting it into Earth system models, whether it is the IIT-MESM, or it is the E3SM, or whichever we're trying to go for, or whether it is a WRF model. How do you start putting these land processes such that it improves the monsoon feedback is a thing going forward? And that's the theme I would encourage all the emerging researchers to look into. Improving predictions of multi-scale processes, understanding the causality between the relations with regards to what's happening from the land processes to the dynamics of the process, creating tools, not just using models, but improving models, and not just saying I created a parameterization, but sort of creating the large data set. I will stop in a few minutes, I guess, or maybe I should stop right away.
In few minutes, please. In few minutes. Yeah.
Okay. So I'll just stop up here by saying that there are 5 points I would like you to consider. First is go from instead of global to local to global. That is the first point I'll make. The second point is that a lot of now monsoon research requires information in our backyard. We need to create this really fine scale resolution. Third, we know a lot about the physical processes. What we do not know is how do you introduce human decisions, and how these human decisions will alter the energy balance, the water balance is one of our emerging challenge going forward. And for this, we have to create new data. And I give some examples of that. We can say this is a building, we don't know what is the material of the building, etc. Fourth, AI/ML is going to be a way forward, that is for sure. But how do we ensure open data? How do we ensure reproducibility of the results? And how do we ensure that the manner in which our meteorological community has moved forward by creating these community models retains its identity without everyone saying this is my model and this is my code and this is my black box? That is one of the challenge I think as a community we need to look forward. And the last point I'll make is, even though AI and ML is so attractive, I would say that no researcher should forget that you cannot use it unless and until we have very strong foundational understanding of the physics and the dynamics of the problem. And without this, we are only going to create more black boxes, which are not going to be a step forward, but a two-step backward in our ability to simulate monsoons. So with that, I'll thank, and I really appreciate giving me this time. Thank you.
Thank you, Professor Niyogi, for a wonderful talk. So now this is open for questions to the audience. Yes, Rupa Kumar,
Yeah,
please speak up.
thank you, Yukari. Thank you very much, Dave. That's an excellent presentation, and I have not heard such a passionate talk on the role of land before, particularly in the context of the monsoons. I have two probably a bit related questions. We know that the landscape, the land surface, has changed tremendously over the past couple of hundreds of years. And we do have good data sets extending over the last 200 years. So what is the best way to bring out the signature of the land surface changes that we know have taken place? Because in most cases, monsoon looks fairly stable in that, at least in the long-term context. So is there any way to bring out that part? The other one is I can see your focus on the urban land surface changes, but at the same time, in heavily populated countries like India, even the rural landscapes have tremendously changed. Don't we think we should also look at how these changes have affected the monsoon variability?
Thank you, sir. Thank you, Professor Kumar. Great questions. The first question relates to how do we detect? We know landscape has changed, and yet we think the monsoon is stable. And so how do we then detect the effect of this landscape change onto the monsoon? That's a challenge that you're posing. And that's actually fascinating. If we look at monsoon into this singular index, then we will not be able to capture the micro scale changes that have been going on in the landscape fragmentation in terms of the changes that are going on. So I think to understand the effect on the monsoon feedback, it would be better if we also look at the data into that fragmented and much more micro scale. Like if you take out locations and then look at it in the context of changes. So we did that in one of our study. Chandra Kishtawal was a lead on that. And I think Subimal subsequently had a couple of students work on that. So if you just take certain grids where we know we have data and we know we have had a landscape change like urbanization or land transformation, with that land transformation, you expect the temperature change, which we know has happened. But if you look at it around the grids, you can detect the change in the rainfall as well in a very sophisticated manner and a statistically significant manner. Now, so the question then comes, does this scale up? So what we have seen, at least in the case of irrigation, in the case of the northern India, this is so organized that you could see with the shift that has occurred in the irrigation patterns, the greenness has changed. And with that greenness, the monsoon low in that region has shifted, and you could see a change in the rainfall patterns. So these kind of diagnostics, which are really targeted some regions where you know there has been a change in landscape, we can tease out this signature. So now the question would be, how do we start putting this in a more predictive sense? And that's, I think, where some of the agent-based approaches or modeling will kind of come in. As far as your second question, we are talking about urbanization, but what about rural? I absolutely agree. If I had 10 more minutes, I would have probably talked about the things we need to do into the agricultural domain, which I think is a fascinating thing. We have just now started putting crops in weather models. We would love to see the feedback of crops in and the rural development in the context of the weather feedback, and then it as a complete system going forward. But I see a couple of hands, so I'll pause here. I don't know if I'm exceeding my time.
Okay. Thank you very much. I saw Dr. Patanaik's hand, but he.
Then I can otherwise later I can send. I can briefly ask one question if there is time.
Okay, very brief question.
Okay. So Professor Niyogi, it's a very nice talk. As you said that AI ML use, little bit skeptical about that one. So okay, so that's true also because of many constraints. But then which are the area that you think that will give a better forecast in future?
Oh, great question. Let me highlight that I am all for AI ML being used, but I'm saying that it should not be used just blindly, which is sometimes what is happening. It has a great application like we have used here for creating a part of parameterizations. So you have a dynamic model. So I think the terminology people use is physics guided machine learning or physics guided AI. Those kind of approaches are well accepted as a good way forward. And I think we should encourage that part. Specific to forecast here, I would say that many of our models are very sensitive to some of the parameter choices we use. I'll give a simple example from something I understand. There is a term called canopy resistance that is used as a function of land use type in every model that is running right now, which uses land. That canopy resistant term has two values, 60 seconds per meter, 100 seconds per meter, depending on whether it is a crop or agriculture. We know that is not right. And yet we have not been able to modulate it to give us a better parameterization constant. And so we can use some of the data set to create some of these constants to be much more dynamic by use of AIML. Or we could use it to simplify a more complex model like a convection scheme to come up with a more simplified representation to hasten and create more ensembles out of it. So those are the manner in which I think people have really found some good examples of progress. And I do hope that once you have a good model and an expert like you, and if you can just work with some of the modules, those could be expanded and improved further.
Thank you, sir. Yeah.
Sure.
Thank you again for your wonderful talk and good discussions. So let's move on to the next talk. Next talk will be by Professor Hatsuki Fujinami. Dr. Hatsuki Fujinami is a lecturer of the Institute for Space Earth Environmental Research, Nagoya University, Japan, and a member of Asia-Australian Monsoon Working Group of GWEX Climate Monsoon Panel. His research interests include understanding the processes responsible for precipitation variations in monsoon Asia over a broad range of timescales from diurnal cycle to climate change. Okay, so his talk is precipitation and its variability in the high elevation area of the Nepal Himalayas. So, Dr. Fujinami, please start.
Thank you very much for Yukari-san. Can you see my slide?
Yes, it looks fine. Yeah.
Okay, thank you very much for a nice introduction. I am Fujinami from Nagoya University, Japan. And first of all, thank you very much for inviting me to such important international workshop on monsoon. It's a great honor for me. The title of this presentation is Precipitation and its variability in the high elevation areas of Nepal Himalayas. They are collaborator working on this topic. Oh, this is outline of this presentation. At first, I'd like to introduce our observation going on in eastern Nepal Himalayas. And based on the observational result, I'd like to talk about two topics in the presentation. One is Diana cycle of presentation that induced by land surface effect in the higher elevation by the glacier area. This is a photo of one of our site. And the second one is a heavy rainfall event that is induced by monsoon low and the typical intra-seasonal oscillation influences. And finally, I will give a summary. A hydrological cycle in the Himalayas is characterized by large amount of summer precipitation, especially in the eastern, central to eastern Himalayas. And there are glaciers, and these glaciers are summer accumulation types. So summertime precipitation is crucial for glacier mass balance. And there are headwaters of major rivers such as Ganges and Brahmaputra, and they provides important water resources for the people who live in the South Asia. However, precipitation amount itself and its variability in summer are still poorly understood because meteorological stations are extremely scarce at the higher elevation in the Himalayas. So we are conducting a HYPLEX. HYPLEX stands for Himalaya Precipitation Study and the Asia PEX project to understand summer precipitation and its variability in the higher elevation of the Himalayas. And this is an international joint research project between Japan and Nepal, and this is a project period. The Northeast, almost all period is affected by COVID-19, unfortunately, but we make best of this opportunity, of course, safely. And this project is performed by using its observation and satellite, GPM and TRAIM and Meteosat and the 5 reanalysis and some cloud resolving regional models. Okay, this is the language network of our project along Lorwarin Valley. Lorwarin Valley is located here in the northeastern part of Nepal Himalayas. There are 8 language stations along the valley, and upper 2 sites are automatic weather stations. And the network covers from 1,000 meters above sea level to 5,500, like this. And this is the photo from Google Earth around upper 2 site here. This is the Zololpa Glacier Lake, the biggest glacier lake in the Nepal. And this is Turakarudin Glacier and Tramba Glacier. You can see the two upper site located by the glaciers. Unfortunately, AWS2 doesn't work well so far. Okay, let's see the result of interesting Diana cycle based on the AWS1 observation. This is the time series, Diana time series of precipitation, and this is local time. We can see 2 peaks in the precipitation. One is daytime, and the other one is nighttime. The daytime precipitation peak is accompanied by valley wind induced by surface heating, so it causes condensation along the slope. On the other hand, in the nighttime peak, we cannot see any significant signals at the surface meteorological element. It indicates large-scale low-level monsoon flow to the south of the Himalayas might be an engine to enhance nighttime precipitation. Similar Diana cycle, such as twice daily maxima, was already reported in the past field experiment like this, and the Kumbh Himalayas and Yara glaciers and Martian river basins like this. Okay, let's expand our viewpoint from one site observation to whole Nepal Himalayas. This is the result from cluster analysis of diurnal cycle of rainfall frequency based on long-term twin precipitation radar data set to see if the twice daily maxima are unique to the high elevation area or not. This is the distribution of clusters. We can see the region of red colors and yellow colors at higher elevation. In contrast, at the lower elevations, we can see the area of blue colors. Diurnal variation in the higher elevation of red color and yellow color shows twice daily maximum, similar to the AWS1. In contrast, at lower elevations, diurnal cycles show only one nighttime peak from midnight to early in the morning, like this. Freeze. Oh, just a moment, please. Oh, sorry. Yeah. This figure shows latitude local time cross section in the precipitation properties to see the contrasting features in the two peaks. This is precipitation. We can see twice daily maximum in daytime and nighttime. And this is precipitation. This is convective type rainfall, and this is stratiform type rain, and this is storm height, raintop height. And from these figures, daytime peak features more convective type precipitation with lower raintop height. In contrast, in nighttime peak, more stratiform type precipitation here and higher raintop height. Okay, let's see the mechanism for driving the twice daily maxima of precipitation based on ERA 5 reanalysis. This is latitude local time section of vertically integrated water vapor flux and its meridional component. This is the Himalayan slopes. We can see the two maximum of moisture flux towards the Himalayas. One is daytime, the other one is nighttime. The timing corresponds to the twice daily maximum precipitation that observed over the Himalayan slopes. The maximum of in daytime is induced by heated slope surface because of anabatic wind, and on the other hand, the peaks in nighttime is coming from the low-level jet process over the Gangetic Plain in nighttime. This is the figure to see the contrasting pattern of water vapor flux anomalies during daytime and nighttime. And this is daily mean field. In daytime, southerly moisture flux appears only around the Himalayan regions because of upslope wind due to heated slope surface. But in nighttime, large-scale moisture flux anomalies extend over Indian subcontinent, including Gangetic Plain, like this. And this large-scale moisture flux anomaly induced large-scale moisture flux convergence around the Himalayas. So this led to more stratiform type rainfall in nighttime. Okay, let's move on to the next topic, heavy rainfall event due to monsoon low through large-scale process. This is based on the observation at the Dongan Station at 3,000 above sea level. This is a daily time series of rainfall in 2090 observation summer, and a heavy rainfall event occur on 8th and 9th July in this summer, this one. This is the hourly rainfall rate during this event. Precipitation rapidly increase at 6 p.m. and reach maximum around 8 to 9 p.m. During this event, line-shaped cloud band passed over the Dongguan station. Stop again. Please wait a moment. Why? Cannot control my slide.
How many slides are remaining? We can share from our end otherwise.
Yeah, maybe it's 4 or 5 slides. Okay. Okay. So, sorry for main trouble. This is already infrared image from Meteosat Eye Indian Ocean data coverage, and this figure shows cloud distribution at heavy rainfall event at 8 o'clock. We can see line-shaped cloud band over the Dongguan station, and there is some strong convection inside the band. So the northward moving line-shaped cloud band with mesoscale systems passed over the Dongguan during this heavy rainfall event. Stop again. I'm sorry. Why? Yeah, this is synoptic scale atmosphere circulation during heavy rainfall event. This is Dongguan station, and this is line shape rain band, and we can see strong cyclonic circulations to the south of the Himalayas, close to the Himalayas like this. This is monsoon low. So during this event, a monsoon low is located to the south of the Himalayas and very close to the Himalayas, and this monsoon low induced large southeasterly moisture transport toward the Himalayas, and the Himalayas slope interaction between the Himalayan slopes and the southeasterly appear to cause the rain cloud and rain band. And the monsoon low or monsoon depression, low pressure systems is major rainfall producing system over South Asia in summer. The effect of monsoon low pressure systems on the precipitation on the Himalayas is to moisten the troposphere, especially in the middle troposphere to the south of the Himalayas, and to enhance water vapor transport toward the southern slopes. It's very important environment to enhance precipitation over the Himalayan slopes. And actually, during this event, monsoon low pressure system is located close to Himalayas. The locations of monsoon low pressure system tend to be specially clustered by the intra-seasonal oscillations, such as boreal seasonal intra-seasonal oscillation (BCSO) and quasi-biweekly intra-seasonal oscillation mode. This is the time sequence of geopotential height and zonal wind at 500 hectopascals. The day 0 is the day of the heavy rainfall event at Dongguan station. This is the monsoon low near close to the Himalayas. And this is day -2, this is day -4, and this is day +2, and this is day 4, day +4. In day -4, there is low pressure area. This is monsoon trough, and the red color indicates westerlies, while the blue color indicates easterlies. And this synoptic situation is coming from northward propagating BCSO mode. And from day 4 to day 0, the westerly areas move northward towards the Himalayas. And please look at here over in the China Peninsula, we can see high pressure system like this, and this high pressure area move westward over the Bay of Bengal as time progresses. So the westward propagating high over the Bay of Bengal push the cyclonic system northward like this. And this westward propagating high is associated with westward propagating quasi-biweekly mode. Yes, this is the final figure. This is a schematic illustration to explain how the combination of different interseasonal oscillation modes such as BCSO and QBW can influence the location of LPS around the Gangetic plain. When the low cyclonic circulation anomalies of BCSO was located here, and the westward propagating anticyclonic anomalies of QBW mode is here. Low level cyclonic wind shear is enhanced around the Gangetic plain. And in addition, the vertical wind shear become also weak. It's a kind of favorable environment for the genesis and tracks of LPS. Okay, this is summary. The meteorological observation at elevations more than 4,000 meters above sea level over the Himalayas is still extremely scarce. So they are essential to understand or monitor the high mountain water cycle with glaciers. And in that cycle precipitation, the twice daily maxima corresponding to day and night occur widely across the higher elevation of Nepal Himalayas, including the glacialized high elevation area. And upslope flow due to surface heating drives the daytime rainfall peak, and the monsoon nocturnal jet over the Gangetic plain creates the nighttime peak. In short, land surface effect is very important to induce dynamic cycle of precipitation in Nepal, in Himalayas, not only Nepal Himalayas, but also other Himalayas. And in the heavy rainfall event, a multi-scale process among the combination of different types of intra-seasonal oscillation and low pressure system and line-shaped rain band and mesoscale strong convection led to the heavy rainfall event at Dongan Station in 2019. The understanding of low multi-scale process from not only topics, but also in mid-latitude are needed to better understand precipitation variability in the Himalayas. Okay, thank you very much. Thank you for your attention. That's all.
Thank you, Dr. Fujinami, for very interesting talk. Because of the time, we can take one quick question from the audience.
If not from the audience, there is a question on the chat box. Can I read it?
Okay. There's a chat box question.
Yeah.
Can it be generalized that the precipitation day-nighttime peak is due to convective or stratiform cloud systems?
Pardon?
Okay.
You.
What is it? Daytime peak convective,
Yeah.
Nighttime peak is stratiform. You mentioned
Yes, this one.
Yeah.
Yeah, in nighttime, more stratiform rain.
Yeah.
Yeah, there's both convective type rain and stratiform type rain, but yeah.
And in that case, the radiative effect can enhance the nighttime rain.
At present, I don't think this is coming from radiative fault or radiative type cloud. I think this is coming from large scale moisture convergence along the slopes.
Okay.
Yeah.
Okay. Thank you very much for a very nice talk. Okay, then let's move on to the last speaker, Professor Chidong Zhang. Are you here? Okay.
Yes, I'm here. Can you hear me?
Thank you. Hi. Yes. Professor Chidong Zhang leads the Ocean Climate Research Division of the NOAA Pacific Marine Environmental Laboratory, PMEL, in Seattle, Washington. He joined NOAA in 2016 after his 20-year academic career in University of Miami. He received PhD in meteorology from the Penn State University, master's in meteorology from the University of Utah, and bachelor from Peking University. His research interests include tropical large-scale air-sea interaction and intraseasonal variability, especially the Madden-Trudeau Oscillation, weather-climate interface, field observations of weather-climate processes, and new observing technologies. Thank you for coming, Chidong. So could you please
I'll share my screen.
Yeah.
Okay, I'll do that. Okay, 1 second.
The title of his talk is Air-Sea Transition Zone in the Context of Monsoons.
Okay, it says it's still connecting. The internet connection is not very good.
Okay.
By the way, greeting from Tropea. I'm in a small town on the west coast of Italy where I'm traveling through. The internet connection is relatively weak, so it still says connecting. So let me see what I can do. Okay, 1 second. What do you see?
We can share. We don't still see the. Yeah, it's coming.
You can see that? Okay.
Yeah. Fine.
Great. Let me see what I can put in presentation mode. How about that?
Yeah, it looks fine.
It's good. Okay, so I'll start. Good morning, everyone. In my talk, I'm going to introduce you maybe a new concept, maybe not, which I refer to as the air-sea transition zone. And because this is a monsoon conference, so I'll start with the monsoon, but this concept is not unique to monsoon. It applies to all air-sea interaction scenario. So these two schematic diagrams, just two examples showing how important air-sea interaction is to all the monsoon. In this specific case, is for the Indian monsoon. We all know that the water vapor source mainly come from air-sea interaction, and air-sea interaction also changed the circulation pattern. And in many cases, the air-sea interaction not only affect surface, but also affect circulation far away and in the upper troposphere. So talking about air-sea interaction, it means different things to different people. In some cases, when people correlate SST patterns with atmospheric phenomena, they call that air-sea interaction. And sometimes people correlate this atmospheric surface forcing, such as surface wind or energy input, to ocean circulation, and they call it air-sea interaction. And of course, many people run air-sea coupled model and diagnose model results, and they call that air-sea interaction. But I hope you all agree that the core of air-sea interaction is the exchange of energy, momentum, and mass through the interface between ocean and atmosphere. So we simply call it air-sea flux. I think this is probably not new to some of you, that the atmospheric boundary layer is very important to air-sea fluxes. On the left, the figure illustrate when there's a deep convection, then the atmospheric boundary layer will be affected by many processes related to deep convection, such as convective downdraft, treatment, and so on and so forth. That will change the surface property of the atmosphere, and in turn will change air sea flux. On the right-hand side, the figure shows that in non-deep convective regime,
sorry for interrupting. I think you have shared your presentation in your PC and you are watching your screen. Actually, organizers have shared the presentations on behalf of you. Can you go to the WebEx meet and?
Okay. Oh, so you are showing the presentation.
Yeah.
Okay, so I'm
audience are seeing
slide number 3.
Number 3. Okay.
Yes. I'm sorry, I didn't realize that. Yeah, here we go. This is it. Yeah. So the left is deep convective regime. The right-hand side is the shallow convective regime. The general message is there's a very dedicated and complicated structure in the atmosphere that it would influence the air's interaction. Next, please. So in the ocean, we also know that the upper ocean structure is also very complicated and important to air sea fluxes. For example, we know we have fresh lands due to precipitation. We have a barrier layer due to the vertical stratification of salinity, and then we have thermoclining. So these are all very important to how ocean structure affect SST, then in turn affect air sea interaction. Next one, please. Typically, if you are an oceanographer, the most common practice is to look at air sea fluxes and then look downward to see what happened in the ocean. And if you are an atmospheric scientist, and typically you look at the surface flux and then you look upward to see what happened in the atmosphere. Very, very rarely, actually, we look surface flux and connect the surface flux to both the upper ocean and the lower atmosphere, especially the boundary. Next, please. So this schematic just demonstrates that there is so many processes in the upper ocean and in the atmospheric marine boundary layer that would affect air sea fluxes. And if you take the upper ocean air sea interface and the marine atmospheric boundary layer as a whole, you can define this as air sea transition zone. The key point is this is a single identity, not a sum of the 3 different components. So that's the concept I want to introduce to you. Take the atmosphere, boundary layer, air sea, and upper ocean as a single identity, which we can refer to as air sea transition zone. Next one. Okay, so once we define air sea transition zone, I would suggest we will redefine air sea interaction. So based on this air sea transition zone concept, air sea interaction does not happen only at the air sea interface. It actually happens through the entire column of the air sea transition zone. That means we have to consider the upper layer, ocean structure. We have to consider what happened at the air sea interface, and we have to consider what happened in the atmosphere boundary layer. And the whole thing together will define air sea interaction. So this is my main message. I hope from now on, the air sea interaction is something happened in the entire air sea transition zone. Next, please. From observational point of view, to observe the entire air sea transition zone is very difficult. The most common practice will be use research ships. And from research ships, you can observe the atmosphere boundary layer, use all different kind of traditional instrument, radar, soundings, LiDAR, and so on and so forth. And you can also observe upper ocean structure using CDTs and using other new instruments. That is one of the standard way to observe the air sea transition zone. And in most, I would say in comprehensive air sea interaction field campaign, we all have this component. Next one, please. Hit again. Yes, no, yeah, this is good. Another way to observe the air-sea transition zone is through aircraft drop zone. So you can drop the atmosphere drop zones and you can drop the ocean drop zone. So they can measure simultaneously the atmosphere profile and the upper ocean profile. So in this way, you can observe the entire air-sea transition zone at the same time. These are the two available way to observe the air-sea transition zone. They share the same issues. Number one, they're very, very expensive. Number two, logistically, they're very challenging to arrange. So we have to look beyond this traditional method to see whether there's other possibility to observe the air-sea transition zone. Next, please. Okay, so this illustrates some available observing technology and some possible observing technology in the future. So if let's go from left to the right, excuse me. On the left, that's all existing technology. So we have drop zone in the atmosphere, we have buoys, we have sail drones, that's the red symbol. And in the ocean, we have ocean gliders, we have the other floats and the drifters, so on and so forth. So those are the existing capability. Then you move to the right one. Actually, we already start to put some more sophisticated instrument profiler on buoys. For example, you can put upward-looking LiDAR to observe the wind structure in the boundary layer, and that has been done for the offshore wind industry. And you can put a sophisticated instrument to look the entire vertical structure of the ocean. Then you move further to the right, and you can imagine we have an air drone. We can have a marine platform. The air drone can take off and landing on the platform to observe the vertical profiles of the boundary layer. And then you move to the far right, you can imagine we can have some futuristic technology. For example, we can have a robotic camera that can stay on the surface to measure surface flux, take off into the air to measure the marine atmosphere boundary layer, and then submerge into the ocean to observe the upper ocean structure. So those are all the possibilities. Next one. So what we can do now, I can introduce you something we have done, not in the monsoon study, but in tropical cyclone study, that we have tried to use the sail drone, which is a robotic surface vehicle, teamed up with the ocean gliders. And just in that case, we observed both the air-sea interaction at the air-sea interface and the upper ocean structures. And then we add on top of that aircraft drop zone, so we can have the vertical profile of the atmosphere. But in the future, we're going to try to add the uncrewed air drones and to team up with the sail drone at the surface and ocean gliders in ocean. So in that case, we can observe simultaneously the entire vertical structure of the air-sea transition zone. Next one. So this is basically my message, is from now on, probably to advance air-sea interaction studies in the monsoon cases or in general cases, probably we should go beyond the traditional air-sea fluxes. We need to observe upper ocean air-sea fluxes and atmosphere boundary layer at the same location at the same time. And that require some new observing technology. Some of them we already have, some of them probably will have in the near future. That's my talk. Thank you.
Thank you very much for very interesting and stimulating talk. So it's open to questions from the audience. Oh, is there any questions? I'll check that. Okay, it is very stimulating. Are you planning such kind of field observation in near future?
As I mentioned, in 2021, we already used the sail drone, and the glidars to observe the hurricanes. And in this coming year, we're going to add air drones, and in the future depends on the technology development. So we're going to continue practice this uncrewed or robotic measurement of the entire air-sea transition zone in the field campaign.
Okay, great. And how long can you observe? What is the span of the such kind of observation?
Okay, the sail drone can stay in the water up to 12 months if it receives enough solar energy, because it's driven by solar energy and the wind. So in the tropics, that's not a problem. The ocean glidars typically stay in the water from 2 weeks to maybe 1 or 2 months. Now the weak point is the air drone. The air drone time span is relatively short, and we do not have the air drone that can fly from the ocean platform. So currently, we're trying to experiment the air drone that launched by aircraft. So we have this small air drone launched by aircraft, then you can control it. So that's our next plan. And I think eventually in the future, we should have some air drone that can, as I said, can land on the marine platform and take off automatically.
Sounds great. Yeah. So you can have a good span of experiments. Okay.
Right.
Thank you very much again for a great talk. And I would like to thank all speakers in this session for providing very good talks and good discussions. So this is the end of this session. So Patanaik, yeah. Thank you very much.
Thank you, Yukari madam. Yes, very nicely conducted session, and we had also very wonderful 4 talks. So it is very. So we'll meet again for the parallel session in Hall A and Hall B. That is a 10-15 hours IST and 4:45 UTC. Till that time, so for 5 minutes break, 5 to 7 minute break. So we'll split now into parallel session A and B. Thank you.
Thank you, everyone. Bye.
Thank you very much.
Thank you.
हेलो नो जैसे
ठीक है साहब।
नमस्कार नमस्कार। जस्ट मतलब चेक करने के लिए कि मेरा पीपीटी इसमें चल रहा है कि नहीं, मैं करूं क्या?
अब कर लो, 2-3 मिनट गैप है, कर लो, टेस्ट कर लो।
अभी ये मैंने शेयर किया।
हेलो नमस्कार साहब, आए क्या? आएंगे कब? ठीक है
ठीक है, स्लाइड शो में देखो। या ठीक है, चेंज करो, दूसरे पे जाओ।
थैंक यू मैडम।
यस फाइन।
मैडम
ठीक है सर, थैंक यू सर। ओके, थैंक यू सर।
One more thing, sir. When you go to the full screen, there is a box coming. Minimize that box also.
May I try again?
For put in the full screen.
Oh, that has gone. Everything has gone. Good.
We can see your presentations. Okay, no problem, sir.
Now you can see.
Yeah, but there are two boxes actually, one in the right, one on the top.
Yeah, correct. You can minimize it or you can close it, no issues.
Okay, this one I will close, no?
You can close.
Okay. When I will start my presentation, at that time I will close it.
Yeah, fine.
Okay, sir. Thank you, sir.
sir, everything fine?
Hello, sir. Good morning.
Yes,
Yeah, nice to see you.
Yes, sir. Thank you. Thank you so much. Thank you so much. Namaste, sir. Hi, sir.
Ramesh, you can unshare your both.
Yeah, you can answer, please.
Yeah, fine.
So now let us start this parallel session hall A. So now may I request Dr. A.K. Sahai sir to kindly chair the session. And as you know, Sahai sir doesn't need any much introduction. Yes, he is very familiar face in extended range, and he has set up this thing, contributed WWRP, WCRP, many leading committee members. And this is the thing, yeah, you can see his biodata. And S2S project, he is involved in many things. Got also many awards, MOS award, MOSAM awards, ITM Golden Jubilee Award, Silver Jubilee Award, and also best research paper for weather and climate sciences. So I'll just not waste much time. So now it is over to Sahai Saab to kindly start the proceeding. Thank you, sir.
Thank you, Dr. Patnaik. So there are actually 6 talks in this, and I hope all 6 persons are there. So the time given is 10 plus 2 minutes for discussion. If they will take 12 minutes, then there will be no discussion. So try to put it in your things in 10 minutes. So whether Sunita Pillai is there?
I'm here only. I'm here only,
Okay.
sir.
So you can start your presentation.
Yes, sir. Yes, sir.
Yeah.
Is it my presentation is visible?
Yeah, go to PowerPoint.
Yes. Yes. Yes.
Yeah, it is fine.
Yes, sir. Good morning, everyone. Thank you for the wonderful opportunity to interact with all of you. My name is Sunita. I'm from Department of Meteorology and Oceanography from Andhra University. Today, I'm going to present some of my results on Indian summer monsoon onset and the role of upper air circulation. so this is the motivation for my study. As you are already, we know that Indian monsoon onset is significantly delaying, and sometimes it's too early and sometimes it's too delay, and it is mainly modulated by the ENSO and IOD phenomena from the Pacific Ocean as well as the Indian Ocean warming conditions. You can see that from 1971 and 66, the mid-latitude tropical waves are much more influencing on the pre-monsoon conditions, which is one of the significant influence on the monsoon onset. The movement of the quasi-stationary waves also, like through troughs and ridges between 55 degrees north to along 50 degrees longitude, and there is a blocking high over the European area is also influencing on the monsoon. By considering of all these facts, that in the present study, I'm going to study the basic physical mechanism why the delay and early onset is happening, with special reference to the mid-latitude. In the present study, the shifting of the convective activities and the tropospheric temperature gradients and the moisture transport, which is associated with the upper and lower level circulation, and all these studies are confined to this monsoon onset areas, and also anomalous changes in the medianal Hadley cell circulation is also studied, and the relationship the convection and SST before the onset is also well studied through in the present delay and onset years. This is the schematic representation of the monsoon onset date, and you can see that the 1st June is the date for where we are receiving the monsoon onset over Kerala region, and subsequently this is the literature review, because for studying of any of the understanding of the physical mechanism we need the literature. So monsoon onset is the one of the most singular weather phenomena over Indian region. It begins on 31st according to Ananthakrishnan and Soman and Kumar, but the main artery feedback, what is the moisture feedback, is coming from the 900 hectopascal through the cross equatorial flow as well as the low level jet stream activity, and that enhancement of the onset vortex is also based on this low level jet. And there are a lot of studies which contributed significant increase of the net enthalpy, latent heat energy, and Arabian sea intensification of the cross equatorial flow, subtropical ridge shifting. And apart from that, several scientific investigations also contributed the monsoon onset activity using dynamical parameters like vertical integrated moisture flux, normalized precipitation index, OLR. According to the Goswami and Xavier, they emphasize the change of the mid-tropospheric meridional temperature gradient is one of the basic parameter to define the monsoon onset vortex. So these are the data sets that we consider for the monsoon onset. Monsoon onset dates are collected from the India Meteorological annual summer monsoon reports and also from the past literature to define the normal onset and late onset and early onset based on these climatological changes, monsoon onset dates, as well as circulation changes, SST changes. According to the IMD criteria, we adapted this basic criteria. So 1st June is the monsoon onset with a standard deviation of 7 days. From the observations, we came to know that the extreme delay was observed in the 1958, and the extreme early onset was observed 14th May 1968. So the normal onset criteria is taken from 28th May to 3rd June. 33 normal onset years are considered, and between 4th January to 27th May, between 4th May to 27th May, we consider they are the early onset. 19 early onsets are considered, and the late onsets are described in between 4th June to 18th June. 21 late onsets were defined, and apart from that, other analysis fields are also considered, like for example, zonal and meridional winds and vertical velocity, geopotential heights and air temperatures. And apart from that, global precipitation project rainfall data is also considered on daily basis to identify the lead lag relationship between SST and convection. OLR and SSTs are also considered from the NOVA optimum centimeter. These are the dates that we described for the monsoon onset in the early onset, urban onset, and late onset years. This is the methodology we consider. The first one is the vertical integrated moisture transport, VIMT equal to 1/c integral of surface to 300 hectopascal QUDP. And another important one, wave activities flux, is also considered from Takia Nakamura in 2001 to identify the quasi-stationary Rossby wave interaction with the monsoon onset. We want to check the statistical significance also, and we try to composite the late onset and early onset. For this, composite analysis is performed. Lead lag relationships is also performed for the relationship between the SST and convection in the early and late onset. And finally, the correlation coefficient is also identified during this study. So coming to the basic characteristics of the convection and rainfall, this is a quite interesting information. In the early onset, we can see the Western Pacific, Bay of Bengal, and Central Indian Ocean shows highest convection, but whereas the suppressed convection is observed over northwest, and which is very significant at 99%. The contrasting features are observed in the late onset. So the prominent convection is mainly observed over the Arabian Sea, off the Somali coast, and Western Central Pacific Asia, and Northwest Indian region. So coming to the rainfall, you can see the Bay of Bengal receives highest rainfall in the early onset years, but whereas in the late onset years, the Bay of Bengal rainfall is decreasing. This is one type of Mashino-Gill type response which alters the tropospheric temperature gradients. That's why we consider the tropospheric temperature also. So we averaged in the pre-monsoon condition from 600 to 200 hectopascal over a for the early and late onset, and you can see that erosion warming is prominently observed with a rise of temperatures 0.15 degrees centigrade to 0.43 degrees centigrade, and persistent cooling was observed over the northwest and northern Indian area. And these reduced temperature gradients, further maintaining in the late onset years, and a weak warming is observed over erosion regions. So this important signal is which is very confined due to the large scale substance of the anomalous Walker circulation, which induced the sensible heat fluxes and vertical mixing during the La Nino onset years. Past literature is also giving a clue for the delay of the onset is mainly due to the El Nino condition. So the decrease of convection and latent heat release, cloudiness, winds, and surface fluxes, they always alters the temperatures over the Indian Ocean as well as the coming to the low level circulation at 850 hectopascal. You can see that anomalous strong easterlies are prevailing over Western Arabian Sea and northerlies along the African coast, which will be contributing the weakening of the Somali jet stream. And also elongated low level cyclonic circulation is prominent from the Southern Arabian Sea, Central Bay of Bengal. So this is one of the important information in the early onset when we observe this type of signal in the coming days. So we can easily predict that it is one of the precursor for the early onset. But in the late onset, you can see the anomalous weak easterlies are prevailing over the Eastern Indian Ocean. So this is quite dramatic features mainly observed in the negative IOD years. So this weakens the low level circulation. It is further shifting northward over the Arabian Sea. So this is one of the important feature what we observed in the low level circulation. Coming to the upper level circulation, in the early onset years, strong upper westerlies are prevailing, especially from the mid latitude. East of the Caspian Sea brings a lot of dry air and cold air to the northern part of the India with a cyclonic circulation, and especially over the northwest region. This cyclonic circulation is the reason for the break conditions for the over the Indian summer monsoon season, and anticyclonic circulation is also established along the equatorial region. So this will be influencing the low level circulations of the Indian summer monsoon season at that time. So we can expect a break conditions also. So and at the same time, emergence of the strong anticyclonic circulation is also over the Tibetan region is very important because shifting of the South Asian high is also associated with the Tibetan region anticyclonic circulation. So these early onset and these are mainly triggered by the mid-latitude incursion of the dry air in the upper level, which will modulate the circulation in the lower level. So that's why this is a very important information from the upper level circulation. And apart from that, the moisture transport is also equally important to understand after the weakening of the circulation, the moisture transport will be also weakening. So along 20 degrees north to 20 degrees north, this circulation is, this transport is very limited. This is also very much understood in the southwestern Arabian Sea. The moisture transport is very high in the late onset year. So vertical integrated moisture is also very important. The moisture feed is not sufficient from the surface to 900 hectopascal. This could be the reason for the early onset and during late onset years, the shifting of the activities, so maintaining of the metropospheric moisture is also equally important. That is happening in the late onset year. Coming to the equal wave activity flux, there are two types of phases will be there. One is the positive phase and second one is the negative phase. The positive phase is always associated with the eastward propagation from East Iran to the Northwest Pacific Ocean and Western.
Sunita,
Yes, sir. Yes, sir. So in the early onset, this positive phase is shifting to the Bonin Islands, which is penetrating the westerlies from the mid-latitude. This could be the reason for the dampening of the upper level cold temperatures for the West Asia. So the existence of anticyclonic phenomena and subtropical ridge at 50 degrees east is crucial for the Caspian is crucial for the onset phenomena. And coming to the Hadley circulation, dampening is also very important. We can see the weakening of the Hadley circulation is observed both in early onset as well as in the late onset. Coming to the relationship between convection and SST during early onset, you can see that the high SST leads to the enhanced convection, enhanced SST, and whereas lower OLR, that is enhanced convection, is lagging after some time because of the atmospheric asymmetries. And this is the large difference between SST forcing and response time over the Arabian Sea. And this is for the moderate onset years. You can see that this will be happening around 1st June. And coming to the late onset years, this relationship holds good in the mid of the June month. So that's why we are getting a late onset years. So you can see the relationship between the SST and convection in monsoon onset extremes. The quotient of correlation is positive and peak in the early onset years in the early May, and whereas in the late onset years, we can see the delay of the onset. So this holds good. This is the schematic representation of the early onset and late onset using different parameters. And these are my conclusions based on the available monsoon onset. It's already I explained about all this information. And thank you very much for your attention. Thank you.
Thank you, Professor Sunita. Are there any questions?
Yes.
So, if not, let us thank Professor Sunita. And now the second talk will be by.
Thank you so much, sir. Thank you. Thank you very much.
So, Ramesh, can you start your? Professor Sunita, you unshare your.
Yes, sir. I stopped my share.
Okay. Good morning to all of you. Can you hear me? Is it okay?
Yes.
Okay. So I am Ramesh Kumar Yadav. Now I am going to talk about the relationship between Jor high and Indian summer monsoon. So Okay, so we know that during summertime, Azure high in the North Atlantic is much bigger in shape and in strength. So if you compare from winter to season, you can see that in winter in the North Atlantic there is this Icelandic low and Azure high, but with summer it becomes very big and its strength is also very high. So there is a common thing between Azure high and Indian summer monsoon that Indian rainfall that both of them peaks during summer. So I thought that there must be some relationship between these two. And also we know that Indian summer monsoon at the surface there is a strong convergence, and at the upper troposphere there is a large scale outflow that creates a large scale divergence. And also we know that the shift of this divergence will cause the shift of this monsoon, in the sense that the upper level divergence will start this upper level motion, and that upper level monsoon will create lower level convergence, and that convergence will attract this moisture. And again, with this moisture, latent heat and other things will start, and like that, that monsoon will revive. So, so to start means I will start with the climatology. Here in this figure, you can see that this explains the 200 HPA geopotential height and divergence. So over the Indian region, there is a strong, it is showing upper strong divergence because of this monsoon, and this contour represents the Tibetan high. So it spans from northwest of Pacific to this North Africa. And over this region, over Atlantic, you can see there is a strong convergence, and also over this North Pacific, there is a strong convergence over this region because of this Azure high and this subtropical high over here. And this represents the 200 HPA vorticity and 200 HPA wind. This contour represents the Asian jet stream, and this represents the American jet stream. So over this North Atlantic, you can see there are two jet streams present during summer season. And because of this jet stream, north of this jet stream, there will be positive vorticity, and south of it, there will be negative vorticity. So because of this two jet stream, you can see that over this North Atlantic, there is a quadrupole type of a structure. And this type of thing is not present in any part of the world. So this represents that during summer that North Atlantic is more vibrant, and it should be studied, and it is having a potential to influence the weather and climate remotely, means over the other part of the globe. And this shows the 200 HPA Rossby wave source and Rossby wave activity flux. So you can see that this Rossby wave activity flux is rotate along the globe around this 45-degree latitude, and at the upper troposphere where there is convergence over this North Atlantic and North Pacific, that these are the regions of Rossby wave source also, because of this upper level convergence, it will be in the Rossby wave source equation. Divergent is one of the parameter, and because of that, upper level convergence will be the source of that Rossby wave. So, and in this study, I have considered different height for stropopause height. This is because that zonal wind is maximum at 200 HPA, divergent is maximum at 250 HPA, like that vorticity is maximum at 250 HPA, and here buoyant Vessela frequency, which represents the unstable of the atmosphere, is maximum at 300 HPA. So in this study, I have considered different heights for this tropopause, and this is because of this is just to show that So now with the recent data set, recent 4-decade recent data set that is starting from 1979 to 2019, I have done the EOF analysis for this region, excluding this Northeast India because of excessive loading and out of phase relationship with all India rainfall. And that corresponding CC, that correlation with this rainfall, IMD rainfall shows positive rainfall over this western and central India and negative rainfall over this northeast India. So basically, there is a dipole type pattern over this region, and in the recent 4 decades, that monsoon is shifting westward. Now, that correlation with upper 200 HPA geopotential, you can see that these are the center of actions which are showing maximum correlation. This is over northwest of India. This is from over that North Africa, and this is over East Asia. This one over North America, and this one over North Europe. So these are basically the CGT pattern, circumglobal teleconnection pattern, and this is because of this monsoon desert relationship. And here you can see this is new, and this is over this North Atlantic region at the same place where that Azure High is situated during this season. And at the lower troposphere, at the lower troposphere, when I correlated with mean sea level pressure and 800 HPA wind, you can see that again I am getting the significant correlation over North Atlantic that is at the same place over that Azure High. So with the recent data set, recent 4-decade data set, what we are seeing that first dominant mode is strongly related with this Azure High. Now that we know, now I have considered this box over this region, over this mean sea level pressure, and extracted the data just to represent that Azure High, and then again correlated with 200 HPA geopotential height. So you can see that here it is negative correlation, positive, negative, positive. So this basically represents the Eurasian Rossby wave, and over this North Atlantic there is a dipole type of structure. So this is basically because of that. Over this extratropic, the atmosphere is equivalent barotropic, so that the high pressure over this Azure High will be same, will have the same signature at the upper troposphere, and this is over this tropics. So tropics, we know that the atmosphere is baroclinic, so this high pressure area at the surface will become negative pressure area over here. And in the earlier studies, I have shown that this is also the source of Rossby waves over this North Atlantic. And this anticyclone, what it will do, that it will intensify the Asian jet stream which emanates, which originate over this place, over this North Atlantic. And this negative negative anomaly will also intensify the Asian jet stream over here. So, actually, this Azure High is intensifying this jet stream, and we know that jet stream acts as a wave guide. So, this low frequency variability which is introduced into this jet stream will travel from this North Atlantic to North India, and also jet stream is favorable for this Indian summer monsoon.
Try to finish into.
Okay. So further, I have correlated with 500 HPA omega, which represents the subsidence motion, and that is obvious because a strong Azure High means there will intensify this mid-tropospheric subsidence, and that subsidence will intensify this upper tropospheric convergence, and that convergence will intensify this Rossby wave source. And this is 200 HPA and vorticity and 300 HPA burn Wurtzlaff frequency correlation. So here you can see that that this represents basically the Asian jet stream, and because of that, this this it will means that unstable air will be along this jet stream from this North Atlantic to Indian region, and this is the composite for excess years and deficient years. So in the excess years, you can see there is a dipole type structure over this North Atlantic, and these Rossby waves are also strong. And here, because of this dipole structure, this Tibetan high core will be shifted westward, and that's why because that monsoon will be shifted westward. While during the deficient years, you can see that here that the dipole type structure is missing because that Azure high is much weaker, and its expansion will not be up to this tropical region, and also this Rossby wave source Rossby waves is much weaker. So during this deficient years, the influence of this Azure high will be very minimum over this north over Indian summer monsoon. But while during a strong years means that influence will be much higher. And this is the EO analysis over this region. And this second EO analysis represents the second EO represents the similar type pattern, this positive anomaly over here, negative, and this positive. And it is very highly correlated with Azure high. So this type of structure do exist over this region. And for more details, you can just go through this paper. And if you have question, I will be happy to.
Thank you, Ramesh. I don't see there is any question, but it is very good presentation, and a lot of new things are there. So I think we have to go for the next presentation by Varunesh Chandra.
Good morning.
Please.
Can you hear, sir?
Yeah, we can hear, but you share your slides. Yeah, fine. Go to slideshow mode.
Yes, it is visible, sir.
Yeah, now it is visible. Thank you.
So good morning, all of you. My name is Varunesh Chandra. I am PhD student at IIT Delhi. So now I'm going to present the topic entitled Decline in the Indian Summer Monsoon. The monsoon synoptic activity in the response to the Arctic and the Antarctica sea ice melt. So basically, my PhD is related to the how this polar sea ice melt is influencing the tropical climate, like Indian summer monsoon, RTCZ, and a low pressure system. So for addressing this project, I am doing a lot of I'm doing the different type of experiment in which I have changed the sea ice over the Arctic and Antarctica, which I present today, and the other experiment where I have changed the sea ice only the Arctic, and other experiment where I changed the sea ice over the Antarctica. So outline of talk today: introduction, motivation, experiment, details, and the result, and finally I will end up with the summary. So introduction. So I have taken this figure from IPCT 2013. So you can this is the actually surface temperature trend. So you can see here the surface is increasing. Surface temperature is increasing over the whole globe, especially more increasing over the higher latitude in the northern and the southern hemisphere. In the below, this is the time series of temperature of red one is the Arctic and the black ones are global. So you can see here the Arctic warming that twice as fast as the global average. So it's mean the polar temperature increasing is more than the globe. So if the temperature will be increased, so it will be impact on the sea ice melt. Sea ice melt will be increased, so albedo will be decreased. Albedo will be decreased, so it will be effect on the energy absorption. So ocean will be absorb more sorbate radiation. So it will be again affect the heat content. So ocean heat content will be increased. So this heat content will be again the push up the temperature. This is the amplification of warming. This is also known as the Arctic amplification. So if the Arctic amplification will be increased more, so it can be impact on atmospheric circulation as well as the oceanic circulation. If the atmospheric and the oceanic circulation will be disturbed, disturbed, then it can impact the regional as well as the global climate system. So this is the last fourth extreme event. This is a very famous picture from the Uttarakhand floods. So I'm not saying this is extreme event is happening due to this Arctic sea ice melt, but somehow it is related from that. So we have already know that the equator received the most short wave radiation in compared to the polar region. So this actually surplus of energy is transferred toward the pole through the atmospheric and the oceanic circulation. So this energy actually transfer through delta T. This is the temperature gradient. Delta T means the temperature between the equator and the poles. So we have already know the sea ice is melting. So if the sea ice is melt, so polar ocean is more short radiation. If it will absorb the more short radiation, then it can push up the temperature. So polar region temperature will be increased more. So this delta T between the equator and pole, that will be the weak. If the gradient will be weak, then the energy from transfer to the equator to pole, that will be actually decrease. So energy transfer is decreased, so it can affect on the atmospheric and the oceanic circulation. If the circulation will be disturbed, then it can be impact on the regional as well global climate system. So it was our initial hypothesis for doing this project. Now I will go to the motivation. So I have actually put it this result here because it is very similar to my result. So it is published by the Sandeep et al. 2019. He is my supervisor. So actually he showed that in the warming climate, the low pressure system is decreasing and the circulation is also weakening. This is, I have taken the figure from the IPCC A55. In the upper panel, it's showing for the northern hemisphere. In the below panel, it's showing the southern hemisphere. So this is the actually Arctic sea ice section in a different scenario. So in a warming scenario is in RCP 8.5, either that is showing the red. You can see here in the both hemisphere, the Arctic, the sea ice section is decreasing. So this is for motivation for doing this project. So what will be happen if the sea ice melt will be in both hemisphere in the tropical climate? So we have done the coupled and uncoupled simulation from the ANCAR CSM model. There I have changed the albedo over the Arctic and Antarctica. And this is actually these settings are similar to the Louis and the Fedro 2019. So I have already told that I have used the in CSM 1.2 coupled fully coupled model in which I have run the 350 years. I have used the pre-industrial forcing in the experiment. I have changed the albedo over the both hemisphere and run for the 50 years. This actually branch of run up 300 year of control experiment. So this was very coarse resolution, so around the 2 degrees. So it is very difficult to track the low pressure system from these experiments. So we have learned, we have again run for high resolution AGCM simulation around the 50 kilometers with the help of these forcing. So I have taken the sea ice concentration and the SST from the last 10 years from these coupled simulation. Last 10 years, this means 341 to 350. So I have run the 8 assembled runs from the AGCM simulation. So starting 4 assembles for the 4 years and last in 4 assembles for the 2 years. Yeah, I have already told about these things. So this is the 8 assembles starting 4 years runs and the last 4 years for 2 years. So it has been done by the slightly perturbing the initial surface for the both experiments. So I have used the Praveen et al. 2005 2015 tracking algorithm used to track the low pressure system from these experiments. So now I will go to coupled simulation results. So this is the last 10 years sea ice concentration, climatology sea ice concentration, which I have forced to use the AGCM simulation. This is the annual mean climatology of sea ice concentration. So you either shaded one is the sea ice concentration from the our simulation, and this is the black contour is from the head SISC sea ice concentration. So you can see this is from control, this is sea ice melt experiment, and this is a difference. Sea ice melt and control. So you can see the upper panel for the Arctic and the below is this is Antarctica. So you can see here the 50% sea ice concentration decreasing in both hemisphere. And this is the actually seasonal cycle of sea ice concentration over the Arctic and the Antarctica. The solid line is showing the CME 5 sea ice concentration RCP 8.5. This is the actually climatological mean of 2081 to 2100, and this is the blue solid line is from the 1981 to 200, and these were our simulation. So you can see here it is very interesting, and this is the similar pattern with the CME5 in the both hemisphere. And this is the SST from the our coupled model simulation. So you can see this is contour is showing the control SST sea surface temperature, and this started on the difference. So you can see here the warming over all ocean basin with stronger warming over the tropical ocean basin. And this is the actually AMOC, Atlantic Meteorological over circulation for control and the difference. So you can see here that AMOC is weakening the sea ice melt experiment. So I have already told that if the sea ice will be melted, so it can impact on the atmospheric and oceanic circulation. So you can see here the oceanic circulation is weakening. So now it can impact on the regional as well as global climate system. Now I will show the addition simulation results. So this is standard one. This is the LPS track density, JGS mean assemble mean LPS track density from the hour simulation, and this contour is showing from the ERA interim. And this is the sea ice melt, and this is the difference. So you can difference plot in, you can see that LPS track density is decreasing in the sea ice melt experiment, and it is also showing a north-south dipole-like structure in the track density change, with strong weakening over the south and strengthening over the north. It is very interesting because it is very similar to result with reported by the Sandeep in 2018. I have already showed in the earlier, and this actually result suggests that response of monsoon synoptic activity to polar sea ice melt is similar to its response to increase the radiative forcing. And this is the number of LPS days. In the LPS days is also decreasing in compared to the control simulation. And this is the category of different storms. So you can see here low depression, deep depression, and the cyclonic storm and subcyclonic storm. So low and depression, it also decreases. This red one from the sea ice melt experiment. So you can see here low and depression is also decreasing in the low in the sea ice melt experiment, but deep depression there is not much changing. This is the actually this vector is showing the wind, and the standard one is showing the absolute vorticity. So you can see from the control, and this is from the sea ice melt experiment, and this is a different. So you can see here the circulation is also weakening and the absolute vorticity is decreasing. So we have already know that the absolute vorticity is very necessary for the genesis of low pressure system. So it is the main reason for decreasing the low pressure system.
Let's try to finish.
Okay, sir. Okay, sir. So and this is the JGS mean assemble mean relative humidity as the 50-100 hectopascal. So you can see in the upper panel is the relative humidity, and the lower panel is the vertical wind shear. So you can see here there's a difference of absolute vorticity. There is the decreasing over the Bay of Bengal and Arabian Sea, but it is not significantly decreasing over the monsoon low pressure genesis location. So this is not contributing to the weakening of LPS activity in the CAM 5 experiment. But if you will see the wind is vertical wind shear, this is the strengthening over the region of the low pressure system. So these results suggest that the stronger vertical shear also has play a role in the weakening of LPS activity in the sea ice melt experiment. So now as a summary, the global sea ice melt is shown to affect the tropical climate primarily through the ocean dynamics. Our results show that the Indian summer monsoon circulation would weaken the significantly in the response to the global sea ice melt. Further, the monsoon LPS that are responsible for the more than half continental Indian rainfall weakened and undergo a northward shift in the sea ice melt simulation. The changes in the low level absolute vorticity and the vertical shear over the Bay of Bengal explain the changes in the LPS activity in response to the polar sea ice melt. Overall, the changes in the Indian monsoon circulation and the LPS activity in the response to polar respond to the polar sea ice melt. Overall, these indicate that the polar sea ice melt might amplify the effect of radiative forcing due to the enhanced greenhouse gas emission. So thank you so much for listening. Thank you.
Okay. Thank you, Varnesh. So this polar sea ice melt you have shown for both the poles actually.
Yes, sir.
Okay. So in the global warming scenario, monsoon will be weakening.
Yes, sir.
Good. Any question?
But sir, this is only the isolate effect of the. I have only changing the, not changing the any greenhouse gas anything. I am changing.
Yeah,
the,
fine,
this
fine,
is actually
fine.
effect of the sea ice melt on tropical climate only,
Yeah,
not global warming.
Okay. Thank you.
Yes, thank you.
So, is there any question from anyone? No. Okay. So the next, thank you, Varnesh. So next talk
Thank
will
you.
be
Thank you so much, sir.
by Hirokazu Endo. Can you start? Yeah, fine.
Can you hear me and can you speak?
We can see.
Okay, so okay.
Yeah.
Yeah. So I start my talk. So thank you, Chairman. Hello everyone. My name is Hirokazu Endo of MRI in Japan. Today's my talk is different future changes between early and late summer monsoon precipitation in East Asia. East Asian summer climate is characterized by the Meiyū rain band. That is one of the Asian monsoon phenomena. The rain band is formed by interaction of low-level monsoonal flow with the upper-level East Asian westerly jet, and the rain band migrates northward from May to July in East Asia. Due to the existence of the rain band, a lot of monsoon rainfall is observed not only over the continent but also over the ocean, including Japan. A recent study shows that East Asian westerly jet anchors the rain band by advecting warm air at mid-troposphere to induce adiabatic upward motion, and also by guiding transient disturbances. Here, I briefly review studies of future changes in Asian summer monsoon. Asian monsoon precipitation is projected to increase overall, and its change rate is larger than that in other monsoon regions. A moisture increase due to a warming enhances monsoon precipitation, while stabilized atmosphere has negative impact on precipitation change through a weakening of monsoon circulation. However, the negative dynamic effect is much smaller in Asia than that in other regions, resulting in a remarkable increase in precipitation. Actually, low-level monsoonal flows are enhanced near the Eurasian continent. The following studies revealed a significant role of land warming on the Asian monsoon response. Coupled model projects a remarkable upper-level warming in the tropics and a tropospheric warming over the Eurasian continent. The upper-level warming that is explained by a uniform SST warming weakens monsoon circulation. However, tropospheric warming over the continent that is explained by a direct effect of CO2 increase enhances monsoon circulation through intensifying the land-sea summer contrast. We have conducted global warming projections with a high-resolution MRI AGCM for obtaining reliable future projection of extreme phenomena and regional climate. The AGCM is hosted by prescribed SSTs that comes from observation or AOGCM anomalies. This EMIP type experiment can avoid large biases originating from the SST bias in AOGCM, enabling us to obtain realistic regional climate. From here, I will show you the result. We conducted 2 sets of ensemble projections to cover a wide range of uncertainties. First is a multi-SST ensemble that covers various SST change patterns in CMIP5 projections. Second is a multi-physics and multi-SST ensemble where 3 different cumulus convection schemes and 4 different SST patterns are employed. The result shows that summer precipitation is increased overall, but there are large subseasonal and regional variations. In June, the Meiyu Bayou band is intensified and its eastern part shifts southward, which are robust within the simulations. In July and August, precipitation is increased over northern China and neighboring seas, while precipitation change is small over the Pacific in August. However, in July, there is no consensus on the projection of the Meiyu Bayou band. In order to understand these future changes, we conducted sensitivity experiments with AGCM. The experiments are designed to isolate 4 kinds of factors listed here. The first factor is the direct effect of greenhouse gas increase, which is often called the first response, which warms the land and consequently enhances the monsoon circulation. And the other factors are SST-related changes, which is often called the slow response, and which is separated into 3 parts: uniform SST warming, and SST pattern change in the tropics, and SST pattern change in the northern hemisphere. This is the result of precipitation change. In June, the response to all forcing is mainly explained by the effect of the uniform SST warming and the tropical SST pattern change. However, in July and August, other factors, greenhouse gas-induced land warming and the SST pattern change in the northern hemisphere are influential. So the result suggests that the relative importance of these 4 factors is different between early and late summer. This is a response of upper level westerly jet that is important background in seasonal migration of the rain band. The total response has a clear seasonality. The East Asian jet is strengthened and shifted southward in June, while it is somewhat weakened in late summer. The sensitivity experiments show the uniform SST warming and the tropical SST pattern change intensify the East Asian jet and shift it southward throughout the summer season. However, the effect of greenhouse gas land warming and northern hemisphere SST pattern change this effect emerge in late summer and oppose and exceed the effect of the other 2 factors. So this results in a clear seasonality of the total response. So for understanding the East Asian jet response, surface temperature changes are analyzed. Total response shows a clear mid-latitude warming in late summer, which weakens the meridional summer gradient around
2 minutes more. 2 minutes more, please.
Okay, thank you. Which weakens the meridional summer gradient around Japan, resulting in a weakening of the East Asian jet through thermodynamic summer wind balance. The mid-latitude warming in late summer is explained by greenhouse gas-induced land warming and large SST warming in mid-latitude. These changes seem to be constrained by the seasonal cycle of their climatology, with an amplification of the magnitude, especially for SST. These changes are possibly connected via land-atmosphere-ocean interactions. So in summary, future projections with the MRI AGCM show summer precipitation in East Asia will increase overall, but large subseasonal and regional variations are noted. In early summer, The simulations consistently project intensified Meiyubai rain band with its eastern part shifted southward, where the effect of SST warming and tropical SST pattern change dominate. In late summer, precipitation is increased in northern China and neighboring seas, while there is no consensus on the projection of the Meiyubai rain band in July. We found the effect of greenhouse gas-induced land warming and large SST warming in latitude are important for these changes, and they oppose and exceed the early summer effect. Our study highlights a distinct seasonality of future changes in East Asian summer precipitation, which is explained by the balance of these four factors, and the results suggest a competition between the opposing factors makes the signal of the Meiyubai rain band response smaller in July than in June. Yeah, that's all. Thank you.
Thank you, Hirakazu. Are there any questions? No, okay, thanks. Thanks for a nice presentation.
Thank you.
The next presentation will be by Dr. Sushmita Joseph. So Dr. Joseph, please, you can start.
Is my screen visible?
No, not yet. Yeah, now it is.
Okay.
Oh, again, yeah.
Okay. So, greetings everyone. Myself Susmita Joseph from Indian Institute of Tropical Meteorology, Pune. My talk is on the changing characteristics of monsoon intra-seasonal oscillations in a warming climate. So, this paper is published recently in TAG, and these are my collaborators. So the motivation behind the study is that in the recent periods, the global warming has risen substantially, and a few recent studies indicate that the Indian summer monsoon is also showing an increasing trend in the recent period. And they attribute this to the rising trend in the warming land and oceans. So in this backdrop, it is expected that the monsoon intra-seasonal oscillations, which are the building blocks of Indian summer monsoon, would also exhibit spatial and temporal variability, and there could be an increased frequency of the extreme events. So here we can see that in the recent period, so this is the difference between the recent period and the earlier period. So here you can see that both the seasonal rainfall as well as the intra-seasonal activity, they both are sharing a commonality in their spatial structure. So there are many studies who have analyzed the meso characteristics in the recent periods, but none of them have checked it in the basis of the duration of these spells, that is the short duration and long duration active break spells. So in this study, we want to examine the changes that happened in the short duration as well as the long duration active break spells in the early 21st century compared to the late 20th century. So this is the year-to-year variability in the number of short and long active break spells during this period. So here we can see that the long spells have increased in the recent period, both the number as well as the number of spells, number of days as well as the number of spells. And the number has increased for the break spells as well. But when we go to the short duration spells, we can see that both the actives and breaks are have reduced in their number, and this decrease in the short actives is 49%, and the increase in the long active is 42%. So these are significant. Coming to the breaks, both the increase in the long duration spells and the decrease in the short duration spells are 32%. So coming to the composite rainfall anomalies for these long and short active break spells for the two periods, and the lower panel shows the difference, that is statistically significant values are only plotted here. So here we can see that in the recent period, there is a intensification of the positive rainfall anomalies over this western parts of the country, and this is also there in the long duration spells compared to the previous period. So if this in the recent period, that the short duration spells are much more intense over this region. So coming to the break spells, we can see that we don't see much difference in their spatial pattern. But when we see the long breaks, we can see that a slight weakening of this break spells is seen over this western parts. This figure shows the Hadley circulation during these two periods, and here also we can see that this in the late periods, that is in the recent period, the intensification is there more over this region, and we can see that there is even the difference also shows that there is an increased ascent over this around 20° north, which was consistent with the previous figure. So in when we see the break spells also, we can see that especially over the long spells, the break spells have weakened over this western parts, which we were seeing, that is to the 20° north. So this also confirms the intensification of the active spells and weakening of the break spells around this 20° north in the recent period. So coming to the moisture as well as the vertically integrated moisture transport up to 500 HPA. So this in the recent period, we can see that the moisture transport has increased much. And if you remember, last day Dr. Patnaik had given a talk that he also told that even over this Arabian Sea region, the moisture transport and is more over this region, and this is giving the more number of spells over this region. So here when we see for the short and long active break spells also, we can see that when we are going for the difference, there is an increased moisture over this region, over the western parts. This also supports that the break spells are weakened over this region. Coming to the low-level convergence and upper-level divergence. So low-level divergence convergence has also increased over this Arabian Sea, and it is slightly not that strong in the Bay of Bengal region. And coming to the upper-level divergence also, we can see that over the Arabian Sea, it is there, but for the Bay of Bengal region, the upper-level divergence has decreased. So these factors can actually decline the formation of the monsoon low pressure systems as well as their further intensification into the monsoon depressions, which could also lead to a reduction in the occurrence of active spells over this central and eastern parts of the country. Now, another thing which we noticed in our study is that the active and break spells, the long spells are more in the recent period. So we just analyzed what could be the reason for this lengthening of these spells. So here we can, this is just the sparse spectra of the JJS rainfall over the monsoon zone region of India. So here we can see that in the earlier period, the power was not that much and the periodicity was also less. But in the recent period, we can see that both the periodicity as well as the power of the JJS rainfall has increased. So when we see the OLR anomaly over this Indian region and adjoining regions, so he can see that in the recent period, that is there is an alternating pattern of positive and negative anomalies over this equatorial region. And there was some earlier study which showed that the equatorial MGO plays an important role in lengthening the break spells. So we just wanted to see whether this MGO is having any role in this lengthening of this active as well as break spells. So we just plotted these Euler anomalies. And when we see closely over the equatorial region, especially the east-west circulation over the 5 north to 5 south region, so here we can see that there is an alternating pattern of the negative and positive Euler anomalies and corresponding to the suppressed and increased convection. So this could be an indication of the eastward propagating MGO in the equatorial region. So further, we plotted the hormonal diagram for the different regions, that is the 5 south to 5 north average. So here also we can see that in the recent period, there is an alternating pattern of positive and negative convection anomalies, and this is also there. They are not much stronger in the short spells and also in the earlier periods. So then in that earlier study, we had shown that the MGO is a Kelvin-Rossby couplet. And so when this is moving in the equatorial region, the divergent part of the Rossby wave that moves to the Indian land and couples with the already existing break condition, and it was intensified. So in similar lines, we plotted the westward, we can see the westward propagation over this region, because earlier figure we have seen that there is an elongation of this rain bands, that is the quadruple structure we generally call. So that is evident for these two spells, both long actives and long spells, break spells. So here we can see that this westward propagation is there from the maritime continents to the central Indian region. So that when couples with the already existing anomalies over the active or break spells over this Indian region, so that gets intensified. So we were wondering why this MGO is having a role in the recent spells or the lengthening of the spells. So we just saw the wave number frequency spectrum analysis of this is the seasonal feature. So for the 2 periods, and it is clearly indicating that in the recent years, the MGO has indeed intensified, and even the westward component is also much more stronger compared to the earlier period. So in the recent, there are some recent studies which shows that because of this global warming, that the SSTs has warmed up in the warm pole region, and here we can see in this figure also that is over this region. This is the place where the MGOs are much more stronger and evident. So here, because of this increased SSTs over this region, there are more prevalence. There is more prevalence of this equatorial MGO. And this could be the reason why we are having more influence of MGO over the
two more minutes.
Yeah. So these are my conclusions. So this is already described that there is an east-west asymmetry in the rainfall patterns, and this was explained because of the increasing temperatures over the oceanic and land areas. There is an increased diabatic heating over the western parts, which in turn increases the instability and moisture convergence and moisture transport. This further intensifies the circulation and rainfall, leading to the intense and long-living active spells and total break spells over the western region. Coming to the long duration spells, as I told, the MGO has an influence, and they influence the northward propagating active break spells through the westward moving convergent or divergent Rossby waves emanating from this Kelvin-Rossby couplet. So this can lengthen the active and break spells. So, but we also understand that the monsoon is a complex system, and it has a lot of interactions involved in that, and a combination of different favorable and unfavorable factors could be instrumental in generating these observed features. And so the dedicated sensitivity experiments using the models would be required to bring out the role of each of them in regulating these characteristics, which is not being addressed in this present study. Thank you.
Thank you. Thank you, Susmita. Now, whether there are any questions? I don't see any hand. Yeah. Okay, thanks for a nice presentation.
Thank you.
And now the last presentation is with Dr. Professor Pradhan Parsarthi. Please. Okay, there is one question for Susmita by Damodar Bagle. Please. Damodar, please unmute yourself and ask if you have any question.
No, sir. No, I have no question.
Okay, fine. Thank you. So now, Pradhan, you can start your presentation. Professor Pradhan, share your. First, you unmute yourself.
I am audible?
Yeah, now you are audible.
Okay. The slides is visible?
Yeah, visible, yeah.
Okay. So thank you, sir. So my talk is mainly focused on the evaluation of Indian summer monsoon in simulation of CIMIP 5 experiment. As many of us, we know that there is a continuous experiment has been conducted under the CIMIP 5 Climate Model Intercomparison Project Phase 3, 4, 5, and 6. So the whole gist of this talk is based on that. There is if you simulate the SIMI-5 experiment and the historical experiment and evaluate the Indian summer monsoon rainfall as well as wind circulation, year-to-year variation during the monsoon season, it is almost you can catch. But when you go on the intra-seasonal scale, which is very much important for the agriculture purpose and water purposes, so it is hardly few models are able to catch the intra-seasonal variability of Indian summer monsoon rainfall as well as wind and relative humidity, because wind circulation and relative humidity is two important factors which is normally responsible for the monsoon rainfall over the Indian continents. So the whole talk is focused on this idea. So the first slide is focused on the climate model intercomparison phase 3. What I have done, I have taken three cases. One is SIMIP-3, SIMIP-5, and again in SIMIP-6. In SIMIP-3, we have conducted and carried out we have analyzed the data of historical experiment for the certain time periods under the SIMIP-3 experiment, and we have selected these five models. That model was available, output of that model was available during our analysis, and we have examined the strength and variability of Indian summer monsoon circulation and ISMR in selected SIMIP-3 model simulations. We have used the mean wind at 850 hectopascal, 200 hectopascal, as well as we use the ISMR, IMD observed ISMR for the degree 1 degree and 1 degree, as well as we use the ECMWF reanalyzed wind data at the resolution of 1.5 degree to 1.5 degree. And this is the very well known monsoon homogeneous zone provided by the IITM Pune. So what we have done, this is the first figure is the area average mean JJS rainfall millimeter per day during the 1961 to 1990 in IMD observed and model simulations. If you see that we have selected the three regions: peninsular India, West Central India, and Central Northeast India. The purpose of selecting these three regions is that there is the very less variability of rainfall over these regions. So first, I was interested to see this, how the model is performing where over this homogeneous monsoon regions when the rainfall variability is very less. So you see that black one is your red one is your IMD observed rainfall, and how the other model is varying in against the IMD observed rainfall. And the second picture, this is the difference in mean JJS rainfall for the peninsular India, West Central India, and Central Northeast India regions. And if you see that there is the very less variation is found over the Central Northeast India. So over the homogeneous CNI regions, the mean ISMR in June, July, August, we have not considered the September months. In simulation of CCSM3, ECHM5 and GFDL 2.1 shows good agreement with the IMD observed rainfall. So this region is in SIMIP-3 experiment under historical experiment. The three models are very much close to the IMD observed rainfall, especially over the Central Northeast India. Now, the 850 hectopascal wind and 200 hectopascal wind has been compared, model simulated under historical experiment. Wind is compared with the ECMWF reanalyzed data. And what we found that the first picture A is for the ECMWF reanalyzed data, and other is B, C, D, E, and F for the other models. So at 850 hectopascal, the position and magnitudes of southwesterly wind in GFDL and these models seems to be close to the reanalyzed values. But they are not exactly following the magnitude and position of the southwesterly wind or Somali jet, what we can say. And this is for the 200 hectopascal wind over the Indian subcontinents. If you see the nearby the in a peninsular India and some parts of the Indian Ocean, the highest magnitudes that is shown in the ECM-WF realized data is 21 meter per second, but it is hardly captured by any other models. Although they are also, the position is little bit shifted in other models. This easterly jet over this region is not being well captured by the other models, especially one or two model is able to capture. So at 200 hectopascal, the Sterling jet of 21 meter per second over Indian Ocean in ECM-WF reanalyze is well simulated by this model, ECHM and GFDL model simulations only. Again, as we know that the vertical wind shear over the box of 5 degree to 15 degree north and 40 to 70 degree east, that is given by B.N. Goswami, that is used for the analysis of Indian summer monsoon rainfall. So this is for the ECM-WF and other models. And if you see that over the base, for the baseline, means under the 1961 to 1990 periods, under the historical experiment, this is comes under the 30.1, and this is hardly captured by any other models. Either it is underestimated or overestimated by other models. Only ECHM5 and GFDL is little bit close to these values. So the estimated vertical shear of zonal mean JJ wind over the Arabian Sea in the ECM seems to be close to the ECM-W analyzed data. It seems that ECHM simulations out of the all considered models shows a good agreement with the observed rainfall and realized vertical wind shear. And this paper has been published in Global and Planetary Changes in 2012. At that time, there was a very limited models was available for the analysis of the global Indian summer monsoon under global warming conditions under historical experiment. Now, after that, we use the CIMIP-5 model data, and we use the almost 34 climate models data to evaluate the Indian summer monsoon under historical experiment for the period of 1961 to 2005. And basically, we used to evaluate the rainfall and wind circulations. And this is the picture of annual cycle of the rainfall millimeter per month over the Indian land regions of all models in historical experiment under CIMIP-5. There is the broken one is the observed IMD, and the observed GPCP is given in the broken line red color. So if you can see that hardly any model is able to capture the peak of the IMD observed or GPCP rainfall. So annual cycle of simulated rainfall in 34 climate model of historical experiment in observation of IMD and of GPCP, it is difficult to get information about a particular model. However, it may be summarized that how well each model simulated rainfall is comparable with observation of IMD and GPCP. Sorry, we could not find any model directly approaching and being close to the annual pattern of the monsoon rainfall, annual cycle of the rainfall. Now, again, we have tested this model by using the Taylor diagram under the historical experiment and compared with the IMD and GPCP in these two figures, A and B. This figures, I'm sorry, this figure is these pictures and is not very much clear. And what we got that CIMIP-5 model simulated rainfall of historical experiments is validated with the observed rainfall IMD and GPCP, and found that these models BCC, CCSM, CESM1, 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 different version of the CESM1 and MPISM1 shows closeness with the observations of the IMD and GPCP. Again, the another way of evaluating this model is the box diagram, or this is the whisker plot, which is used in the statistical analysis for the statistical analysis. So this is all the correlation with the CIMIP model simulations in IMD observed and GPCP observed and this is the RMSC for CMIP 5. And the variation of correlation and RMSC in observation and historical experiment is shown by box plotting. The spacing between the different parts of the box indicates the degree of dispersion, spread, or skewness and outliers in the model simulated rainfall. And the simulated rainfall approaches to GPCP observation with greater correlation and lower RMSC, while it is not well captured in IMD observations. So this is the very important findings, that when we are evaluating the global climate model, they are hardly being close to the IMD observed rainfall. They are normally becoming close to the GPCP rainfall. So again, we have evaluated these models for the wind circulation at 850 and 200 hectopascals, and these are for the NCEP wind for the 1961 to 2005, and these are the models which we have used and selected for our analysis. And similarly, this is the mean JJS wind at 200 hectopascal for the period of 1961 to 2005 in historical experiment. Again, this is the 21 meter per second. It is hardly represented by any other models in the historical experiment. Only I found that MPI model is relatively giving better performance than other models in CMIP 5 experiment. Although the data or periods you are taking under consideration is very important when you are doing the climate analysis, model output climate analysis. But based on this period 1961 to 2005, this is the fact that the models CCSM4 and MPI are able to reproduce JJS wind at 850 hectopascal and 200 hectopascal. Yes, I will complete it very soon. Okay. And this is the intra-seasonal variability of Indian summer monsoon rainfall in CMIP 6 model simulation. This paper appears in the Theoretical and Applied Climatology in 2021. What we have done, we have details of these two models. We have taken different versions of these models, and we have tried to analyze the relative humidity supplied by the Arabian Sea and as well as with the Bay of Bengal regions. And we found that in July and August, the simulated wind in MPI and MPI shows resemblance to the reanalyzed wind. However, the reanalyzed and simulated relative humidity over the Arabian Sea is relatively less than those over the Bay of Bengal. And the reanalyzed relative humidity over the Arabian Sea is close to the simulation of in BCCSM in JJSM. It seems that the simulated relative humidity shows proximity to the reanalyzed value in June, but failed to capture in July, August, and September. Over the Bay of Bengal, the variability of reanalyzed relative humidity in mean JJS and individual months is well represented in the simulation of BCC CSM2 MR model. And this is the annual cycle for the IMD M1, M2, and M3 model. M1, M2 is represented by this model for the June, July, August, September. And this is for the rainfall distributions. So our findings tells that in CMIP 3 and CMIP 5 models are well performed on the intra-annual scale when there is the season to season variation in one season in 1 year and next season in next year. But when we come on the intra-seasonal scale or monthly scales, the models are almost failed to represent the wind circulation, monsoon rainfall, summer monsoon rainfall, and relative humidity. So these are the weakness of the climate models. Until unless we do not correct the representation of this wind circulation, relative humidity on the intra-seasonal scale, always we can get an error in output of these climate models when we analyzed or evaluate the historical experiment data for the Indian summer monsoon regions. So this is my presentation and this is my thought. Thank you very much.
Thank you, Professor Pradhan. Whether there is any question? Okay, Professor Pradhan has analyzed from CMIP 3 to CMIP 5, 6, all, and he has come to some conclusion. So overall, there were 6 presentations in this session, and all presentations were very nice, and almost all are published also. And they have also shown the climate change and how dynamically it is related and all those things in changes in precipitation and other things. So I think this was a very useful session. Now I'm handing over to the organizers.
Thank you, Sahaj Saab. Yes, it was a very good session, and the time also you maintained very well. And all the speakers, all 6 talks, I was also listening. They are very excellent result for climate change, monsoon variety, extended and prediction. So it is a wonderful session. So thank you very much to you as well as the speakers. Again, now we will come back to Hall A for the short oral presentation that will be up at 11:45 local. That means that is 11:45 is 6:15 UTC. So till that time, bye for now. Thank you.
morning, Dr. Patnaik, sir.
Good morning, good afternoon, and good evening, wherever you are. So welcome to the fifth day, 26th March, this hot oral and composter session. So this is the last poster session of this workshop. So there are total of 16 people present, I think 16. Yeah, total 16 people provided their presentation, and some of them not yet submitted their presentation. Therefore, first we'll be completing all those 16 in sequence. Then afterwards, if time permits, and if somebody is really interested to present, then he or she can present here, but only 1 or 2 slides. So now we'll be starting this session with first Hussein. So from the organizer side, the presentation will go on, and one after another, the presentation will be done, and you have to maintain the time. Will be allotted with 2.5 minutes, and then another half minutes or minutes so for a quick question. Then we'll go ahead with that, like that. So be precise and complete your whatever the study, only covering the objective methodology of your study and a few salient results. So that is what you must complete within this presentation. So start with will be inviting Resma Madam. So our presentation is trends and variabilities of Indian summer monsoon rainfall in different intensity bins over West Coast and monsoon corridor. So Madam, start.
Okay, sir. Thank you, sir. The major objective of this paper was to analyze the long-term trend, long-term variability of the summer monsoon rainfall and the rainfall patterns in 6 intensity bin over the West Coast and the monsoon region in India. And we also investigated the relationship between this region summer monsoon rainfall in different rainfall intensity bin with the global SST. Next slide, please. So for the analysis, we have used the gridded rainfall data from IMD and the sea surface temperature data from Met Office Hadley Center, that the hard ISST data. The period of the analysis was from 1901 to 2020. And the season was JJS, or the summer monsoon rainfall. The region selected were West Coast, the coastal strip of the Indian Peninsula region, and the Mansoor corn zone. So in this study, we have classified the rain events into 6 intensity bin based on the percentile value. They are dry, low, moderate, high, very high, and extreme intensity bins as shown in this slide. And we have analyzed the trend and the significance of the trend using sense slope estimation and Mundt-Kendall test. And we also done a correlation analysis in order to evaluate the strength of relationship between the rainfall and intensity bin in both the regions, how they are correlated, and also to investigate the relationship between the global SST and the rainfall and its intensity bin. And we also done a 31-year sliding correlation analysis to check the consistency of the relationship of global SST with the rainfall and its intensity bins. So in the result, we have seen that the West Coast show an increasing trend in total summer monsoon rainfall over the season, and the monsoon course showed a decrease in rainfall with a 90% confidence level. And in the west coast, the extreme intensity bin show a significant increasing trend of 6.18 millimeter per season per decade. And in Monsoon Onset, the low intensity bin show a increasing trend of 1.98, and the very high intensity bin showed a decreasing trend of 2.62 millimeter per season per decade. This is also at a significant of 90% confidence level. Then while looking to the strength of relationship between the rainfall in both regions, we have seen that all the intensity bins showed a significant coherence or in-phase relationship in both the regions for the whole period 1901 to 2020. But for the extreme intensity bin, the relations were not coherent. And in order to check the time-wise variation in this, we have done a correlation analysis in 4 multi-decadal period. That is, the 1901 to 2020 period was subdivided into 4 multi-decadal period with each having 30-year time period. And we have seen that the extreme intensity bin in both the region was showing a negative correlation over the first 3 multi-decadal period. But in the last or the recent multi-decadal period, that from 1991 to 2020, the extreme intensity started to show a significant, that is under 95% confidence level, a significant trend positive correlation. And towards the recent decade, multi-decade, majority of the intensity bins, that is dry, low and moderate, also showed significant positive correlations. And the correlation of summer monsoon rainfall and its intensity bin with west coast and monsoon core zone with the SST in Arabian Sea, Bay of Bengal, North Atlantic Ocean, Nino-3, North Central Pacific Ocean and Southwest Pacific Ocean has also changed towards the recent decades. We have seen that the west coast and monsoon contour intensity bins had showed a significant increase in the correlation. In the recent period, that is from late 1990s and 2000, and also the extreme intensity bin in west coast showed a phase change in the relationship with Arabian Sea SST. So in summary, we can say that there is a significant trend of increasing and decreasing rainfall over west coast and monsoon.
Okay, madam, that's so we have to conclude actually because others will be also presenting. Okay.
Okay, thank you, sir.
Okay, if anyone has a quick question, so please. So if not, so we'll be going to next presentation then, please. So Utkarsh Barma, so he will be presenting revisiting climatological diurnal cycle of precipitation over Indian subcontinent using IMERS data. So now Utkarsh ji. Dr. Barma, you are there? Are you there to present? So if not, actually we can come back again to his presentation if he can join. So we can go ahead. Yeah. So now the presentation is by Gopika Venugopal. So the presentation is dynamic and thermodynamic structure of atmosphere associated with extreme rainfall events over Kerala during August 2019. So continue, please.
Okay, sir. So hi all. So today I am going to present the dynamic and thermodynamic structure of the atmosphere associated with the extreme rainfall events which took place over Kerala during August 2019. So can you move to the next slide? So the 2019 Southwest monsoon season ended with 2 major intense spells of very heavy to extremely heavy rainfall events over Kerala region, and the first intense spell was reported during 19th to 23rd of July, and the second spell was reported during 6th to 11th August. And the second one in August was one of the most severe and catastrophic rainstorms in the state's history. And several studies observed a rainfall of more than 50 mm in 2 hours over many regions of Kerala and regarded it as a mesoscale cloudburst event. And in our analysis using IMD gridded rainfall data, we have identified that an area located over the central Kerala region received maximum amount of rainfall during these days. And considering this particular area as our study region, we have further analyzed the dynamic and thermodynamic mechanisms of the atmosphere from 6th to 11th August. And here in the figure on the left, we have analyzed the 3-hourly march of low-level convergence, upper-level divergence, and upper-level vorticity using IMDA datasets, along with 3-hourly march of TRMM rainfall. And a strong low-level convergence and upper-level divergence is noticed from 7th onwards, which peaks on 8th, and a predominant upper tropospheric cyclonic vorticity is noticed from 8th onwards. And these mechanisms, it can be inferred that these mechanism plays a crucial role for the ascending motion observed throughout the troposphere and subsequent precipitation on 8th August over the study region. And in the figure on the right side, in the top right, we have analyzed the 3-hourly march of Cape and Sine during these days. And even though it was continuously raining from 6th onwards, a sudden increase in Cape is noticed from 7th, and a very low value of Sine is noticed throughout from 7th to 9th August. And it indicates that the near surface stable layer is shallow, or its thickness might be very less, and the presence of a strong unstable atmosphere during these days. And thus, it can be the extreme rainfall event which took place over the central districts of Kerala was triggered majorly by the dynamic forcing mechanism, which has been further supported by the thermodynamic forcing mechanisms. It can be concluded like that. Thank you.
Thank you, madam. If anyone has any question. Madam, actually, I have one question. You have not actually told about your study domain. In this parameter, yeah.
Sir, I have mentioned it in the poster. Here it is. There is no space for.
Okay, just okay. What is that? Can you?
Sir, it was over the central Kerala region between 10 to 11 degree north latitudes.
Okay. Okay. Thank you, ma'am.
Okay, sir.
So will we go to next? Yeah, one announcement is that these presentations are going here, but all those posters can be available in our website of the conference workshop. So please visit the site and see the poster for more detail. Here only 2-3 minutes. They are not able to cover everything. So please visit the site and for detailed poster. Okay. So Dr. Bharadwaj, please continue.
Thank you, sir. In this study, we are targeting the inter-annual scale of variability for seasonal rainfall and the temperature in the India for summer and winter season. That will take into account the varying length of the season. Next slide. So in this study, we utilize the IMD gridded rainfall analysis data, which is available at quarter degree resolution for more than 100 of years, and surface temperature data, which is available at 1 degree resolution, and ERSST data, which is available at 2 degree of resolution from 1969 to 2005. So in this study, the varying length of the season are defined based on Noska and Mishra 2016 paper. In this, we computed the onset and demise of the summer and winter season from daily rainfall and surface temperature respectively. In the figure 1, if you see this is one of the grid point rainfall amount has been plotted, and you can see that the blue dot curves are basically showing the very robust features of rainfall since India, major rainfall over India happens during JJAS season. So what features we can draw from this bulge shape? So what we have done in defining objective and demise of the season is based on the climatological rainfall over a grid point, there will be a negative contribution. If you see the red curve, which is a cumulative anomaly curve, so if the rainfall amount is less than the climatological rainfall, it will contribute negatively, and it will go to the minimum location, which is whenever there is a rainfall amount more than the climatological values. So onset is the next day after the minima, and demise is when the rainfall goes less than the climatological value. Similar way, the winter season, in this case, we cannot define based on the rainfall, because rainfall is not the major contributing factor. So we choose the surface temperature to define the winter season. So similar, if we see figure number 2, from October to May, this is the temperature profile. The similar procedure can be adopted when there is a maximum curve happen, when the climatological values of the temperature is less than the actual values. It will give the positive contribution, and similarly maxima and minima. Based on these two, we can define onset and demise for the winter season, as well as onset and demise for the summer season. So this procedure can be adopted for all the grid points of India. So if you see figure number 3, this figure shows the climatological onset, demise, and length of the season, as well as the seasonal rainfall. The significance of this figure, you can see the local onset.
Conclude, please.
Yeah. So based on this, we can actually compute the seasonal length based on this objective definition. Then what we have done is to get the inter-annual scale of variability.
Amit, conclude.
Yes, sir. So to get the scale of variability, we correlate the seasonal length principal component to the ERS SST, and we found that the winter season is negatively correlated with the tropical SST, as well as the summer season JJA SST is positively correlated. So we can say that by taking into account of the variable length of the season, we get stronger correlation compared to the fixed length of the season. So this way can be adopted. Thank you.
Thank you, Amit. If anyone has any question, quick question. So if not, we can go ahead with presentation. Krishna Mishra. So Krishna, please continue.
So I am going to present comparative analysis of 2013 and 2021 Southwest Monsoon advance over India. In the year 2013, Southwest Monsoon covered the entire country within just 16 days from its onset over Kerala on 1st of June to coverage on 16th of June. In 2021, the onset took place over Kerala on 3rd of June until 11th of June. Most parts of the country was covered by the Southwest Monsoon, except the plains of Northwest India. And after that, monsoon progress became slow till 19th of June, and after that there was a hiatus of 3 weeks from 19th of June to 11th of July. So we have analyzed this all 6 semi-permanent systems associated with the Southwest Monsoon by using IMD bulletins, IMD monsoon report, NCEP reanalysis data, and www.worldmonsoon.org Somali Jet Index. So next slide. Next. So here we can see that in 2013, Somali Jet Index was more than normal throughout the month of June, but in the 2021, during first half of June, Somali Jet Index was above normal, but during second half of June, Somali Jet Index was below normal. Next slide. And here we can see that zonal wind 500 SPH zonal wind, the weekly winds we have taken, and we can see that from 18 to 24 June there was a westerly trough which was mainly responsible for this monsoon hiatus of 3 weeks, and then in the following week there was a ridge in 500 SPA, and again in the following week there was in the figure D there was a westerly trough, and in the next figure E from 9th to 15th of July we can see that a shear zone has developed roughly along 18 degree of latitude, indicating active monsoon conditions. Next slide. Next. And here this is 200 SPA anomaly of GPH anomaly, and we can see that the Tibetan high has shifted northeastwards, indicating weaker monsoon conditions. Next slide. And this is the masculine high shifting southeastwards to its normal position. According to Gray and Sikka, this leads to weakening of the Somali jet. But the heat low over Pakistan is close to the normal value, so we cannot conclude from heat low any weaker monsoon conditions. Next slide. And this is the MJO according to Pai et al. Phase 2, 3, and 4 are favorable for southwest monsoon active southwest monsoon conditions. And here we can see that MJO lay in phase 1 during June 20th to 30th, and it came in phase 3 in second week of July. That's all. Thank you.
Okay, thank you. If anyone has any question, so for details, please visit the poster. So if not, then we'll be going to next presentation by Arijit Datta.
Hello, good morning, everyone. So today I'll be talking about the AMO monsoon teleconnection, focusing on the Eurasian.
Is it a bit louder?
Yeah, can you hear me, sir?
Yeah, now it's fine.
Yeah, so today I'll be talking about AMO monsoon relationship, focusing on the Eurasian teleconnection. So can you go to the next slide, please? Yeah, so there is a known relationship between the mid-latitudes anomaly and Indian summer monsoon on subseasonal and internal timescale. For example, if you see the figure, when we talk about the strong and weak West Central Asia years, in the left we look into the upper level anomalies in 200 millibar. So when the ISM impact is included, and in the right, when we exclude the ISM impact, we see that there is a feedback from ISM on interannual timescale. So this relationship is actually getting modulated on multi-decadal timescale. So in the right, we see the 200 millibar geopotential height associated with AMO, and we see that there is an arcing wave pattern that resulting in upper level anomalies over West Central Asia, the black box region. And in the time series, we do see that all these three climate phenomena, including AMO, the West Central Asia anomaly, and ISM, are showing coherent multi-decadal changes. Although in recent decades, AMO and monsoon, there is a difference in the relationship, which is possibly related to the Pacific influence. So we see that there is a ISM and WCA is actually interacting in interannual time scale. And we see that on multi-decadal time scale, this is again impacting ISM. In the bottom left figure, we see the regression of West Central Asia index on the 200 milliwatt geopotential height. We see that there is a similar signature what we saw in the interannual time scale. So what it causes easterly shear over the Indian domain, which is causing the instability during the monsoon. So this is actually revisiting the AMO monsoon teleconnection, focusing on the mid-latitude anomalies. So the interannual relationship between the ISM and the mid-latitude anomalies is getting modulated on multi-decadal time scale by AMO. Thank you.
Thank you. If anyone had any question? If no one had, I have one simple question that
Yes,
have you checked that when ENSO weak and ENSO that Illinois is weak and Illinois is strong,
yes.
whether this relationship is altering or it is
Yeah,
maintaining
so
the
on
same?
interannual timescale, there is not much sensitivity on ENSO. Actually, there is on paper by Ding and Wang in 2005, they talk about that also. So that's in line with.
Okay. Okay, we'll be going to next presentation then, please. Lakshmi, is there?
Yes, sir.
Yeah, so please present.
So here I am going to present the study on the extended range prediction of Madden-Julian oscillation using IATM-CFS version 2 model and the role of initial error on the prediction scale. So there is a widely accepted hypothesis that improving these initial conditions can improve climate model's performance in a longer lead time. So the objective of this study is to find whether this hold for the forecast scale of strong MJO events during MJJAS in the IATM-CFS version 2 model, and also the source of large model error cropping up from the initial lead days itself during some few of the initial conditions are also identified in this study. So next slide, please. So the convection and the propagation characteristics of MGO has been captured using OLR, zonal winds at 850 and 200 hectopascal. The data used were NOAA interpolated daily averaged OLR and the NCEP reanalysis data set for the wind variables. And the model data was obtained from CFS version 2 hindcast of IATM extended range prediction system. And so the multivariate EOF analysis has been done following the Wheeler and Hendon method 2004. And the EOF was calculated by using a period of data from 1979 to 2018, and the analysis was done for the period from 2003 to 2018. The EOF1 represent the enhanced convection over the Indian Ocean, and EOF2 is in quadrature with the EOF1. And for this analysis, strong MGO events were considered. From this, two set of events were identified, one with the least error in initial day, that is light cases, and the one with high a set of events with the highest error in the initial days, that is high cases. From the results, we can see that the first figure shows bivariate RMSE and correlation of light cases and height cases. So from a week to 10 days, after a time of week to 10 days lead, we can see that both the set of cases are having a similar bivariate RMSE error. And going to the second figure, it shows the error growth, that is error in day n minus 1. So in this also we can see that the light cases are having a high error growth for the initial few days, that is up to 7 to 8 days as compared to high cases. But later on, both the set of cases are having a similar error growth pattern also. While seeing the probability density function curve of this error growth as in figure 3, the first shows the density curve for the initial 10 lead days, and the second one shows 10 to 20 lead days. And for the first 10 days, we can see a slight difference in the peaks, but for the second lead days, we can see that both the light and height cases are showing a similar density distribution in the error growth also. So both the error and error growth of light and height is similar after a lead time of 7 to 10 days. So moving on to the sources of the high error that is cropping up from the initial lead from in light cases. So the figure 4 shows the PC amplitude error distribution for the initial day phase and the lead days. So in here we can see that those events with initial phase over Indian Ocean and the Western Pacific are having a high error in the PC amplitude. So next slide, please. And this shows the spatial distribution of the first one shows the spatial distribution of upper level winds, and the second one shows first one shows the lower level wind, and second one shows the high level winds. The first row in the first figure shows the light cases, and the second row shows the height cases, similar for the second figure also. In the first figure itself, if you can see the third set of this is arranged in the order of observation.
Just gist of what is those figures are telling. Yeah.
Yes, sir. Yes, sir. So in the while seeing the bias, that is the third set of figures in each of these figures, we can see that for the light cases, the error is getting cropping up after 10 days over the Indian Ocean and the Western Pacific region. But for height cases, from the initial set of initial lead days itself, there is a high error that is being developed in the Indian Ocean and the Western Pacific region. And the similar error has also been observed in the upper level winds also. So summarizing, we can say that the effect of initial error in the forecast of lead time greater than 10 days is much limited while predicting the MGO using IATM CFS version 2 model. And the difference in error growth in high and light cases is related to constraints in model physics. So incorrect model forecast over Western Pacific and Indian Ocean region is reducing the model prediction scale. And the initial improvement of error in PC is not being carried beyond a lead time of 10 days in this model. So more emphasis is to be given to sorting out the biases in model dynamics and physics rather than focusing on improving the initial conditions for the extended range prediction of MGO using this model. Thank you.
Okay, thank you, ma'am. Okay. Anyone has any question?
So this is Ashok Raja. Just takeaway. Is there any particular bias or solution in your mind to take over this problem? Because you have told almost everything is bad. So is there any particular bias which needs to be added into the model dynamics?
No. Actually, the objective of this study is not that actually. Here, ma'am is telling that Lakshmi is focusing that the IC rather IC dependent it is that errors are not very much in IC dependent, rather it is based on problem with the model. Means so whether it may be dynamics or physics. Okay. So
how
it
to
is
correct it,
cause
sir?
of the error where we should focus. That is what it is telling, the study is telling.
Yes, sir.
Okay, we are going to next
okay, sir.
presentation. So Sai Krishna, Dr. Sai Krishna is there.
I couldn't find the author in the participant list.
What is there? To present this paper, anyone is there? Okay, so we are going to next by Mahesh Kalsetti.
Kalshetti. Am I audible, sir?
Yeah, you are audible.
Thank you, sir. Good afternoon. I'm presenting the scale of subseasonal to seasonal forecast model in predicting the eddy forcing associated with the extratropical tropical interaction. As we know that mean flow modulation due to a transient eddy is an integral part of the atmospheric general circulation over the tropics as well as the extratropics. To analyze the significant impact of the transient eddy on the, transient heat flux and transient momentum flux, we use diagnostic tools to get the impact of the transient eddy as well as based on the transient eddy transport indices. The objective of the study will be to identify and address the critical factor responsible for the EDT interaction and real-time rainfall forecast and various aspects of the monsoon intra-seasonal variability with help of the dynamical modeling. Next slide, please. Thank you. In present study, we have used the ERA5 reanalysis data as well as the rainfall from the TRMM, and we tested the forecast skill based on the IITM Airbus handcast. So in present, first figure shows the lead lag relationship between the transient meridional transient eddy transport indices with the rainfall. Here we have the line composite of the standardized rainfall anomaly for the all the instances over the active and break days, first panel in first figure, with respect to the EMF indices, but there are only around 22% of active and break spells are shows the lag relationship with day 0 rainfall over active and break days. Here we use the indices EMF transport, which suggests that if positive EMF transport means the poleward transport of the eddy momentum flux, and negative means equatorward transport of the indices. After identifying the indices, we have tested the rainfall composite, second figure, second row. Here we found that the enhanced rainfall activities over the Gujarat region and over the West Bengal, and subdued rainfall over the Western Ghats as well as the central India. For the break, we have seen enhanced rainfall activity over the northeast region as well as over south central India. Next, we have looked the 2 sigma rainfall analysis under the consideration of the only EMF indices. Here, figure 3, we can see there is a northward propagation of the rain bands of plus minus 3 days. With there is a eastward propagating the gyres, and at the day 3 there is a enhanced circulation which is we call East Asian anticyclone. Then we tested this day 0 rainfall based on the E vector approach and the right right column. So the divergence pattern moving eastward as a day progress. On day 0, there is a strong E vector divergence. James et al. 1994 suggests that if there is a meridional gradient of the divergence of E vector is proportional to the transient eddy vorticity flux divergence. So it induces the anticyclonic vorticity forcing that day 0 it rainfall enhances. Next, we have tested the scale of the handcast for the rainfall for the various transient effect and present of the transient eddies. Here, no transient are known as a neutral condition, and or rest of the 4 for EMF poleward equator transport and EHF transport poleward equatorward. Over monsoon core region, we can see that the rainfall predictability for the equator transport of the EMF is persist up to the 4 week, followed by the neutral condition. Over the northwest region, as we know that it is under the influence of the WT type of response all the year. So only up to the second week scale there is a persist in the this. So in summary, for the first time, E-vector diagnostic tool used for the defining the ADOT monsoonal interaction. Also, active and break spells rainfall patterns associated with the extratropical forcings are presented for the first time. Observation depicts EMF index could act as a 13 days lead precursor for the predicting the tropical phenomena such as the onset of active break spells. Extratropical originated transient can influence anomalous extreme rainfall. And rare 2 sigma North Indian rainfall composite suggests upper tropospheric eastward migrating forcing induces southward upper level anticyclonic forcing, which further uphills the pre-existing monsoon surge. The scale of S2S forecast over the monsoon core zone is not always robust when there is no extratropical transit. Hence, the S2S scale would be improved if the extratropical transient eddies are better simulated. For the further discussion, please visit my poster section. Thank you, sir.
Okay, you covered little more time. Anyhow, still, if anyone has any question.
Yes.
Mahesh, I have one question. What is the period of this transient? Period.
For in present analysis, we use 30 to 60 days transient eddies.
Okay. You can use wavelet actually. Try it. Huh?
Sorry, sir?
Wavelet transform. Using the
I'm not
within those period, you can use the wavelet transform.
Yes, sir. The indices itself is formed with the help of the wavelet transport.
Okay.
Thank you.
Your poster. Okay. Next presentation by Pratibha Gautam.
Yes, sir. Sir, I'm audible?
Yeah, sure.
Okay. Hi, everyone. This is Pratibha Vatam from IITM Pune. Today, I'll be presenting the role of land surface feedback process and prediction skill in S2S scale during the monsoon onset and in the coupled model framework. So the main objective of this analysis is first we will see how the different land surface initialization affect the monsoon onset in the S2S scale, and second we will see how it affects the prediction scale by the land surface parameter. Next slide, please. So for that analysis, we have taken 2 experiments from the UKMO model. In one, they have initialized the soil moisture from the climatology, and soil temperature and snow were initialized from the era interim reanalysis, which is referred as UKMO old. And in the second experiment, they have used land surface reanalysis, which was created by Joule's land surface model, forced by JERA 55 reanalysis, which is referred as UKMO new. So for comparison of the model output, we have taken IMD observation for rainfall, and for other variable we have taken era 5 reanalysis data set, and we have taken monsoon onset dates from this paper, Joseph et al. 2015. For more detail, you can visit my poster in data and methodology part. So So in result, first we have seen that how these two different land surface initialization affect the monsoon onset. So here I have plotted the biases in the rainfall. This first A represent the biases in the rainfall pattern in the UKMO new model, and this is 1B represent the UKMO old, and this is third represent the biases between the two UKMO new as old. Further, we have compared this with ITM CFS model. This is the 1D represent the biases in NCMRWF, and the second is biases in NCEP, and this is the NCMRWF minus NCEP. So we can see that from the rainfall bias, we can see that both the model, if we consider UKMO new model, so we can see that in both the model UKMO new and UKMO old, both are not able to capture the rainfall pattern over the rainfall over that ROK region. So further, we have seen that how this biases in the rainfall is related to the biases in the land surface parameter. So for that, here in figure 2, we have plotted the kinetic energy of rotational component of 10-meter wind and the rainfall pattern. So this is this one is from the biases in the UKMO new, and this is UKMO old for the rotational component of 10-meter wind, and this is the 2C represent the biases in UKMO old and UKMO new. So this is from this. This is from the this is for rotational biases in the rotational component, and this second plot represents the biases in the divergence component. So from this biases plot, we can see that both the model is not able to capture the near surface variable. We can see that there is a huge bias in capturing. We can see that there is a positive bias over the land, and this is the negative bias.
Please
So
try to conclude.
Okay, sir. So we can see that both the biases in the land and ocean are different. So we can see that the feedback is different. Further, we have analyzed its prediction skill in the UKMO model. So in summary, we can see that the UKMO new possesses the better prediction skill beyond the 10 days lead, and we can say that if we have error in the near surface variable like in soil moisture and temperature, if it affect the near surface fluxes like 10-meter wind relative humidity, further it will affect the monsoon onset rate over that region. Thank you.
Thank you. So anyone has any question? Okay, if not, then we will go to next presentation by Devabrat Sharma. Devabrat Sharma, I can see actually in the participant list.
Hello?
Yeah.
Can you hear me, sir?
Yeah, I can hear you. Yeah, please continue
Good
presentation.
afternoon, everyone. My name is Devabrat Sharma. I'm from the Institute of Advanced Study in Science and Technology, Guwahati, Assam. I'm working in the field of long lead prediction and predictability of the Indian summer monsoon rainfall. So the objective of the work that I will be presenting today is based on an method that is used for the true estimation of the long lead potential predictability of ISMR by taking into account the simultaneous contribution from all the 3 tropical ocean basins, that is the Atlantic, Pacific, and the Indian Ocean. So the motivation behind this work is that we believe that in order to estimate the real potential predictability, we need to build a predictor which will take into account the contribution from all the 3 oceans as well as both the tropics and extratropical predictors. So the data that we have used in for this work is the ISMR data we have taken from the IITM data archive. We have taken the sea surface temperature data from the Kobe SST to reanalysis, and we have also used heat content in D20 variables, which we have taken from the simple ocean data analysis version 2.2.4, and we have kept the special field to be between 0 to 360 longitude and 30 south 30 north latitude, so that we can incorporate both the tropical as well as extratropical predictors or the drivers of the Indian summer monsoon rainfall. So the methodology is as follows. So what we do is that suppose we are building the predictors for the D20, and we are building the predictor at a lag 1. So we have built predictors from lag 1 to lag 48. So lag 1 may represents May. So suppose we are building predictions for lag 1, and we will take the May D20 maps for that particular for over a period of 136 years, say, and we will project it on the correlation map with the ISMR, and we will generate the DP predictors. So similarly, we have generated the SSC predictors, which we call as SP, and heat content predictor, which we call as HP. And we found that the correlation with the D20 predictor and heat content predictor of ISMR with ISMR is high, not at short lead but also at long lead. That is around 18 to 24 month lead. But the correlation with the SST predictor with the ISMR is very weak. So in order to understand these intriguing results related to the D20 predictor, we also did a error growth analysis. So which is basically based on the event-to-event variability that we have of the warm and the cool events that is taken from the global recharge oscillator associated with the D20. And so the black curve basically represents the growth of errors or the error propagation with lead month of the warm events, and the red one basically represents the growth of error or error propagation of the cold events. And you can just know that the ISMR is phase log with the annual cycle, and from the error growth analysis we can see that the fluctuation of the error are also phase log with the annual cycle. And from both the peak and as well as from the trough, we can see that at 18 to around 24 months, the error growth is minimum. So these the initial errors at 18 to 24 months represent the initial conditions at which we have achieved such a high potential predictability of ISMR, which is around 0.8 at longer leads.
Now summarize, please.
Yes, sir. So in summary, we will conclude that we need to take the contribution from all the three tropical basins. So we have represented also a graph here where we have taken the Pacific basin only, and when we take the global basin, it makes a huge difference. So the D20 based predictor, which is associated with the global recharge oscillator, is more suitable for the estimation of this potential predictability of ISMR. And since both ISMR as well as the initial error of D20 are phase locked with the annual cycle, we are able to achieve this high long lead potential predictability at around 18 to 24 months.
Thank you. So, any question? Okay, if not, so we will be going to next presentation. Darshana Patikar. So, yeah, Darshana ma'am.
We couldn't find in the participant list then.
No, yes, she is there actually, I can see. Darshana Patikar in the participant list, I can see. Yeah, are you presenting, or we'll go ahead with the next presentation? Darshana madam, you can write in the chat box if you have any technical issue. Please write in the chat box.
Can you hear me?
Yeah, now we can hear.
Can you hear me?
Yeah.
Yeah. Should we start?
Okay. Please start.
Yeah. Hello everyone. I'm Darshana Patikar. I'm working as a research fellow in Indian Institute of Tropical Meteorology, India. The topic of my presentation is subseasonal variability of the Indian summer monsoon rainfall 2020 in observation and CFS to hindcast. The objective is to investigate the possible reasons determining the unusually reduced rainfall in July 2020 in observation and coupled modeling. Next slide, please. The study period is 1979 to 2020. The data taken from SST data is from ERSST. Other variables from NCEP, NCAR, and GPCP rainfall has been used. For this study, the coupled model is used as NCEP climate forecast system version 2 with 9-1 hindcast prepared for 1985 to 2020, which is initialized in May and February. So the 2019 was a weak El Nino year that vanishes quickly in spring season and transmits to La Nina in 2020. Year 2020 is the third highest in all India seasonal rainfall since 1990. High positive rainfall anomalies related to La Nina noticed almost all over India from June to September, except in July. Particularly Specifically, in July 2020, strong negative rainfall anomalies over monsoon trough region from Bay of Bengal to northwest India is noticed. This is mainly because of westward extended anomalous western North Pacific anticyclonic circulation, that is the Pacific Japan pattern in July. So there is interbasin interaction between this PJ mode and the anomalous tropical Indian Ocean warming, which is called as the Indo-Western Pacific Ocean capacitor mode. So here it is important to investigate the role of PJ mode in July 2020. Here the PJ mode is extracted by applying the EOF analysis over the 850 HPA vorticity anomaly in July over the Indo-Western Pacific region, and the corresponding PC is correlated with rainfall and SST and wind at 850 HPA. So we can clearly see the low rainfall over the monsoon trough region associated to PJ mode. Also, the West North Pacific anticyclonic circulations are extended to Indian region, especially over the monsoon trough region. So here we can say that the changes in the West North Pacific anticyclonic circulation associated to PJ pattern are mainly causing the low rainfall in July over the monsoon trough region in the presence of La Nina. The same we can see in SLP signals over the West North Pacific region, which are positive SLP, which are extended over the monsoon trough region. Also, the upper level divergence over the Western Indian Ocean can be seen. Here, if we in 200 HPA wind, if we see the subtropical jet position as compared to June and August, the subtropical jet position is slightly southward, which may weaken the Tibetan high and which further influence the tropical easterly jet and hence have impact on monsoon. So if we see the model hindcast, then unlike observation, model showing low rainfall in June and high rainfall in July. This is mainly because of the overestimated La Nina signal in both May and February initial conditions. Also, the overestimated positive rainfall anomalies are observed over the Indian region in July. Also the anomalous low level WMP anticyclone is missing in both the hindcasts in July. So concluding this session, we can say that the less than normal rainfall over the monsoon trough region in observation in July 2020, it is mainly due to the anomalous westward extension of WMP anticyclone associated to strong Pacific Japan mode, the southward displacement of subtropical jet, and less number of depressions developed in the Indian Ocean during July. The CFSP2 model show low scale in the reproducing month-to-month rainfall variation in summer, and instead both the hindcasts show the high rainfall in July in contrast to observation. So the main reasons for anomalously high rainfall in model is that the highly overestimated La Nina in models throughout the summer monsoon season. Overestimated La Nina controls the upper level and low level circulation anomalies, and also absence of West North Pacific anticyclonic circulations in July 2020. Thank you so much.
Thank you, madam. Okay, we can have a quick question. Okay, so go to next, please. Yeah, Ashok Raja.
Yes, sir, I'm available.
Okay, so start, please.
Hi, I'm Ashok. I'm working as a scientist in hydro division at IMD. So today I'm going to present on the topic of performance of flash guidance system or west coast of India during the tropical cyclone Tauktae. So the prime motivation of the study is to see how R2O process, like research to operation process, and how to see impact-based forecast based upon the thing which was available in our operational platform. So the objective is very clear, to provide location-specific flashback guidance alerts, which is in the form of 24-hour risk and 3-hour threat products. We used 2 regional models and 1 IMD GFS global model. Apart from this, we do also integrated real-time gauge observation, that is 5,500 plus observations, and satellite data, and 17 Doppler data of India. So the study was to see how the performance of this particular system, which was operational in 2021, how the performance gave, which reflect to the impacts in the local level, in the watershed level. So we took the study period between 14th to 19th May. So slide 2, please. Yes. So I will not go into the data, what all we used. You can see from the poster actually. So it has 33 diagnostic products and 18 prognostic products. Also, all these are available with us every 6 hours. And the data goes inside in real-time mode. The hydrologic model here used is SAC SMA. So there are total 1 lakh watersheds as of now, and it is fully operated on a GIS dynamic platform for the operational forecasters. So here in this case, what happened is the cyclone track was given prior to 14th May, and it was continuously tracked by the RSMC bulletins. And we followed when it was in a low pressure system itself. And we also have a hazard map, which is also prepared by IMD. So hazard map is district-wise hazard map based upon the climatological data. And we do have a hourly real-time satellite data, which is being hydro estimator data based upon infrared microwave adjusted. So while following the track of the cyclone, we found out many storm surge activities and many coastal flood occurrences. But in this case, we are going to concentrate only upon what has exactly happened in 2 particular districts. One is in Ratnagiri and another one is Sindhudurg. So what gave us the hint in the operational platform? So all the things which were discussed here occurred in a span of less than 8 hours in the operational platform. So before the start of the intense spill, that is on May 16th, you can clearly see the soil saturation was completely minimum and the FFG values were actually high. And when the rainfall occurred, that was a rapid rainfall, and I will show you how much was the rainfall amount. It started from 6 millimeter and it went up to 36 centimeters, rubbing over all the watersheds of these 2 particular districts. And at 1200 UTC, you can clearly see there is a bunch of soil gets saturated, which is an immense rise. The top 20 centimeter soil and the subsurface is also get saturated, beyond which it goes for the surface runoff. So the flash flood threat and the flash flood risk was also indicated and communicated.
Please conclude.
Slide number 2, please. Next slide, please. Okay, so the results here is we take care of the land surface parameters, atmospheric parameters, and we gave around 60 number of operational alerts for the complete cyclone period. We had many successful studies, and these 2 are the most particular study which has occurred and which has helped the state people and the managers to take away. So the conclusion of the study is how the utility of the GIS platform along with the forecast products in reference to the nowcast from the Doppler weather radar is being properly used in the operational platform by the hydrologist and hydrologist. And to be having a further suggestion, if we include the real-time socio-economic data, it might be much more effective for taking decision-making process at the critical times. Thank you.
Thank you, Raja. So will be this product. So if you can visit poster for details. So we are going to next presentation, please. Yeah, Dr. Reggie. Dr. Reggie.
So he is present or not? I think not.
We are not finding him or her here in the list. Okay. So anybody will be presenting in the from this participant list?
Yes, sir. I am Amuli Ute from IITM Pune. My name is there in the list, but my PPT has not came there. My name is not announced.
No, I'll be coming to the just whoever could not present, I'll be coming to them at the last. So whatever is there in the present, if anybody is presenting this paper. So if not, so we'll be going to next. So, Madam Archana.
Yes, sir. Good afternoon, sir.
Yeah, please present.
Yes. Good afternoon, everyone. Myself is Archana. I am from MIT University, research scholar. Today's my presentation topic is characteristic features of low-level jet in ERA 5 and IMDA during Indian summer monsoon in satellite era. It is the first time we are checking this low-level jet feature in IMDA. Previous mostly papers use NCEP, ERA 5 and all this data, but IMDA is the first our data set which is very high resolution. So we took this data. So objective of this paper is to know the climatological features of low level jet during Indian summer monsoon rainfall season, that is June to September, using two different high resolution reanalysis data sets. So please next slide. So in data sets, this ERA 5 is 0.25 resolution and IMDA is 0.12 resolution, and we use variables like U wind, V wind, R for relative humidity, Q is for specific humidity, and T is for temperature, and MSLP. In IMDA, specific humidity is not present. We calculated using the formula, and for rainfall we use IMD dataset which is on 0.25 resolution. For this analysis, we use student t-test, which is applied to identify where these two data set have there is significant difference or not. So first we check and we find out the statistically significant spatial variation is noted in both the reanalysis data set. Whereas ERA 5 and IMDA both suggested better rainfall patterns over Himalayan foothills during the monsoon season. And also ERA 5 and IMDA reanalysis capture the LLJ features, but the amplitude of wind in IMDA reanalysis data set is lower than the ERA 5 reanalysis. And we check different level like 925, 850 and 700 hectopascal. So in that we find out at 925 hectopascal in ERA 5 reanalysis data, both data sets show substantial increasing trend in wind strength at all study matlab all pressure level, different pressure level. So the LLJ core zone is located between 10 degree to 15 degree north and 15 to 60 degree east, and it is extended vertically up to 700 hectopascal with maximum core winds linearing at 900 to 850 hectopascal. And over the Indian region, ERA 5 performs slightly better than the IMDA reanalysis. For the figures and all more details, please visit my poster. Thank you so much.
Thank you. So no results figure is available, so we have to visit certainly the poster. So any question is there? If not, we will go into next presentation. Yeah, Yagyaseni Das.
Yes, sir. Am I audible, sir?
Yeah, audible.
Good afternoon, everybody. I am Jagyasini Das, research scholar at the Center for Atmospheric Sciences, Indian Institute of Technology, Delhi. I am here to present the role of machine learning for Indian monsoon prediction. Accurate prediction of Indian monsoon is necessary for agriculture, power, and water resources. The objective of this paper is to gain insight into various machine learning techniques and to provide an overview of the applicability of machine learning techniques for Indian monsoon rainfall prediction. Next slide, please. The key motivation to construct a machine learning model is the availability of huge climate data. There are several climate data sets are available comprising of time series data, predictor data,
climate model data, etc. Based upon the requirement, researcher can use the data sets of their choice of study. After collecting the data, then the next step is data pre-processing, which is an important step before applying any machine learning model. Pre-processing of data is necessary to transfer the raw climate data into useful format. For example, data normalization. Then the data is divided into training and testing phases. The machine learning is categorized into supervised learning, unsupervised learning, semi-supervised learning, reinforcement learning, and deep learning. Based upon the requirement, researcher can use the suitable machine learning model. The machine learning based predictive models are built in by following the mechanism of the figure as shown here. First, the past rainfall data is used for training, then data pre-processing techniques are applied. Then the suitable machine learning model is used to build a predictive model based on the training data. The same predictive model is used for predicting the new monsoon rainfall testing data. Machine learning techniques are gaining popularity due to their wider applicability and incredible efficacy to solve a complex problem in an effective way. But their lack of wider application from a climate prediction perspective is a need of concern. The previous studies, as shown in the following table, indicate their potential applicability in Indian monsoon rainfall prediction. These are some of the relevant studies experimented in our laboratory. Initially, we have carried out the study in 2017 by using the IWM time series data for Northeast monsoon rainfall. We have used sea surface temperature and sea level pressure as predictors, and we have used the techniques artificial neural network and extreme learning machine. And we found out that the better technique is extreme learning machine with Radha's activation function, and sea surface temperature is a good predictor than sea level pressure. Similarly, we have done several studies in 2017, 2018, and 2019. All these studies are presented in my poster. Please visit my poster. And these are in 2019, we have used the IITM time series data for Indian summer monsoon rainfall, where we have used the predictor sea level temperature and sea level pressure, and we have used single layer feed forward neural network, extreme learning machine, regularized online sequential random vector functional neural network, and we found out that the better predictor is the combination of sea surface temperature and sea level pressure, and the better technique is ROS RVPL technique. So now coming to the summary. Machine learning models are used for forecasting climate phenomena, extreme weather events, downscaling of climate variables, data assimilation, detecting climate regions, study of climate predictors and their association with Indian monsoon, etc. Still, exploration of potential machine learning techniques for climate science is in preliminary stage, for which there is a dire need for extensive research. Thank you.
Thank you. Very interesting, but you have to look into the extremes actually, whether the performance is good for predicting the extremes. Okay. Thank you, madam. So now we can go to the presenter, whoever
Good afternoon,
will
sir.
be presented in this sequence. So Mr. Dr. Vibhute and Sibin Balakrishnan, two actually reported that they will present. So you can directly present from your terminal or device.
Okay, sir. I am Amul Vibhute. I will. Can I present
Okay,
now?
so Amal, you present then. Yeah.
Okay, sir. I am sharing my screen.
Yeah.
Yes, sir. Is my screen is visible, sir?
Yeah, screen is visible. Make it full screen.
Yes, sir. I am Amul Vibhute working at IITM Pune. My objective is to study the impact of meridional displacement of Asian jet on the Indian summer monsoon rainfall in observations and climate system forecast model. I will go to the next slide, that is data sets used and methodology. In this section and in this study, we have used the atmospheric data from the ECMWF and ERA5 as well as the SST data from ERSST and GPCP rainfall data. The CFSV2 retrospective forecasts are prepared for 9 months and covering a period of 35 years from 1985 to 2019 at IITM. The EOF analysis, correlation, and regression analysis 20 test will be used for this study. I will go to the results. The first figure shows the climatology of zonal wind at 200 hectopascal in the summer months, which shows the strong Asian jet is centered at around 40 degree north in the observation in figure A, and in the same is indicated in figure B for the model. So this the box indicated here is used to calculate the EOF analysis of 200 hectopascal zonal wind, and this indicates the meridional displacement of the Asian jet. The PC associated with it gives the meridional displacement index, and regression of this meridional displacement index with the zonal wind at 200 hectopascal and the total winds indicated in figure C for the observation, and same is indicated for the model in the figure D. So this indicates the Asian jet is displaced southward with strong positive anomalies to the south of the 40 degree north and strong negative anomalies with the north of the 40 degree north. So this southward shift of the Asian jet is highly located over the East Asia than the West Asia, and associated cyclone circulation is also strong in the East Asia than the West Asia. But in the model, this meridional displacement is strong in both in the West Asia as well as the East Asia. Associated and cyclone circulation is also strong in the West and East Asia. So associated with this strong southward displacement, the rainfall is decreased over the central India, and this rainfall decreased is due to the weakening of the tropical easterly jet, and this decreases the rainfall over India. So associated with southward displacement of the Asian jet, the rainfall is also decreased over the India in the model. But this further we have looked into that. The El Nino is influencing more into this. El Nino associated with the southward shift is influencing more to this decreased rainfall. And as well as the rainfall over the Indian landmass is more spatially extended associated with the jet. So for this reason, we have looked into the month-to-month Asian jet variability, where we have seen that the Asian jet is shift from West Asia to the East Asia from June to September, but this shift
conclude.
But this shift is prominent in the June and July in the model, but in the September this equatorial shift is strong in the both West and East Asia. So it is this West Asian this southward shift in the West Asia is contributing more into the in the September is contributing more to the seasonal rainfall, as well as the in the Asian southward displacement of the Asian jet. So my conclusion is the meridional displacement of the jet on the seasonal mean is stronger over the East Asian region in the observation, but which is not well represented in the model. Month-to-month variations of southern displacement of the Asian jet are well captured by the model in June and July, but fail to capture in the other months. So this seasonal rainfall is highly influenced by the El Nino in the model. So I would like to thank you for this for the giving opportunity to present work here.
Thank you. So, Sivin, please make your presentation ready.
Yes, sir. Is my presentation visible, sir?
Not yet. Share the screen, not the application, please.
I have shared the screen, sir.
It is not coming.
Shivin, share the complete screen. not the slide alone.
Okay, Busair, actually, Sai Krishna is writing that he wants to present, his presentation is there in your list. Can you make that
Okay,
part
sir.
ready?
Now or after Shibin?
Sibin is not able to share actually, so we can in between finish Sai Krishna.
Okay, then Shibin can send email to me, then I can present from my side.
Yeah, yeah. In between
Actually,
Sibin,
we are having
please.
ePoster of Shibin. We don't have the PPT of Shibin. We have
Yeah, so
only
Sibin, please, if you have the PPT, send it immediately to Hussain so that it will be presented from this side if you have any technical issue.
Okay.
Hussain, (136) actually. Yeah, this one. Yeah, so Sai Krishna, you continue to present.
Yes, sir, I am ready. Thank you.
A bit
Hello,
loud,
everyone.
please.
Hello, everyone. This is Sai Krishna from IIT Rourkela. Today, I am going to present my topic on impact of spectral nudging in the simulation of summer monsoon rainfall over India. Generally, southwest monsoon receives about 80% of annual rainfall over India. So, skillful prediction is very essential for the crop yielding and social economical impact on the social economic status of India. For this purpose, from last few decades, we are using global general circulation models. Even these global circulation models are up to the mark in simulating the large scale features, and these large scale features. But the rainfall simulation is skill is comparatively poor. So it, it's mainly because of the coarser resolution of the global circulation models. So the next further the downscale approach came to the existence to downscaling the global circulation for global model forecast to forecast in the regional climate models, so that we can improve the prediction rainfall, so that we are improving the rainfall simulation. And similarly, for long time scale simulations in the even in the downscaling approach, we are facing some inconsistency between the large scale features and driving fields. It leads to the climate drift. So that to reduce this, there is a method called spectral nudging is introduced in simulating the ISMR rainfall. In the main objective, the main objective of the study is to evaluate the impact of spectral nudging in the simulation of ISMR variability at seasonal, subseasonal over India and its homogeneous regions. It also assesses the model fidelity in capturing the monsoon extremes such as normal, excess, uh, and deficit years. The next slide, please. For this to achieve this object, we have conducted two experiments by using the ECMWRF data at 75 km as the initial and boundary conditions. And the both experiments we have been updated the SST, and commonly we have we kept constant the parameterization schemes, and we have considered the domain like 10 degrees south to 45 north and 45 east to 110 east. And for validating the for validation to validate the simulated rainfall in the both experiments, we have used IMD data. Coming to the result, we simulate in the result part, the simulation of seasonal rainfall is well captured in the spatial pattern and magnitudes are well captured in the spectral nudging compared to the NSN experiment. In If you see the mean rainfall, we have conducted about 37 monsoon years from 1980 to 2018. The mean rainfall of
all India rainfall is about 6.9 in the IMD, whereas in the spectral nudging it's about 6.7. It is very close to the IMD observation. So we can say we also extended our analysis to the region wise, like homogeneous regions, peninsular, northeast India.
Summarize, please.
Okay, next, coming to the subseasonal scale, we observed very interestingly, we observed the huge variation in the June to July simulation rainfall. And similarly, we observed the RMSE among all the overall all the regions. The RMSE is very comparatively less compared to the non-spectral nudging method. In the interannual variability of ISMR, we divided the normal, excess, and deficient years, and we observed the frequency of the rainfall. And among all these also, among all these
Summarize,
extreme.
please.
Coming to the conclusion, in the spectral nudging, seasonal and subseasonal scales are improved, and the rainfall bias is also rainfall bias and magnitude less less biases are observed, and among about five homogeneous regions are well captured among the six homogeneous. Significant improvement is observed in the first 60 days spectral nudging. Thank you.
Okay, thank you, Sai Krishna. One thing I should say, it is either ECMWF or NCMRWF. It should not be ECMRWF. Okay. Okay, so next.
Oh, sorry, ECMWF.
ECMWF.
Thank you,
Okay.
sir.
So any unshared, so Sivin will be presenting. Yeah.
Oh.
Good afternoon, everyone. Can you make it full screen, Busher?
Busher, go to view.
I will zoom the region as you mentioned.
Okay. Okay.
Busher, go to view and make it full screen. Yeah. This down below. Yeah, full screen. Yeah. So now.
Can you zoom it?
Oh, that was better. Okay. Busher.
The fit to width would be okay. 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 Yeah. Okay. So my this preliminary analysis is with respect to the rainfall event which occurred over Tamil Nadu region during 2015. So this study is.
Okay, Sivin, continue.
Yes, sir. As we all know, major rain-fed monsoon for Tamil Nadu region is during northeast season, where generally the 48% of rainfall is achieved during north of the Tamil Nadu region. So during the 2015 period of northeast monsoon over Tamil Nadu region, excess of 58% rainfall was received. So my objectives of this study, Busher, scroll down. Is to look into the major two events which took over Tamil Nadu region in 2015 of November and December, and specific synoptic patterns associated with that. So to come out with this study, I have utilized two data sets. The one is with the ERA5 data set from the Copernicus portal, and another is the IMDA data set from the NCMRWF data set. So I have taken these data sets and compared it with the IMD graded rainfall. Above Busher, can you just take it above? Yeah, thank you. So coming to the first event which took place in November 2015. So from November 2013, there were trough of low over Andaman Sea which persisted and resulted into low pressure region, and this resulted into the well marked low over Tamil Nadu, resulting into copious amount of extremely amount of rainfall over the Tamil Nadu districts. Approximately around 35 to 40 centimeter of rainfall was received over the coastal districts. So the panel on the left indicates the ERA5 reanalysis data. This is for the 15th of November. The major spells which has occurred from 17 UTC to 24 UTC. So that I have shown here. So you can actually see. Busher, can you just come down with respect to the observe? Yeah. No. Little bit. Just this little bit up. Yeah, thank you, thank you. Yeah, so you can see the ERA5 data showing copious rainfall over southern coastal districts of Tamil Nadu, which is persisting from 17, and we can see the rainfall band which is seen in the ERA5 coming from the Sri Lankan region into northwestwards into the Tamil Nadu coast, whereas that band is not seen in IMDA. So when you compare it with the observational data, which is shown here below, you can see IMDA showing rainfall only along the coastal sides, whereas the inward or the interior, the coastal districts of rainfall is not well captured there, which is seen in the ERA5 data. Similarly, the northern districts of Tamil Nadu, where rainfall was extremely heavy during those periods, so that is visible in the IMDA data sets, whereas in ERA that is missing. Coming to the next extremely heavy rainfall over December 2nd, 2015, which took place. So again here, the major synoptic conditions were the trough of flow which existed over Southeast Bay of Bengal from 28 November, and that again intensified into WML. So there was reports of observation reporting around 40 to 50 centimeters of rainfall over Chennai city and suburban regions. So these plots are again showing
summarize, please.
Yes, sir. Intense rainfall spells during the period in ERA 5 and IMDA. So here again you can see the rainfall is less, or we can say not very well captured with respect to the coastal districts, whereas the ERA 5 has shown a over prediction or rainfall over the districts. So with respect to this study, I've taken few more steps which I have not shown here. So other considering the cases with respect to some similar events of depression or another extreme heavy rainfall events with consignment of these studies, we can kind of come to a conclusion with respect to the data sets. Thank you.
Thank you. So Busair actually.
So Shibin, I have one question. So according to you, which one is the good one, ERA or IMDA?
See, good one in the sense, again, that is what I'm saying. This is with respect to these two cases which I've taken, and I have even seen with the upper level vorticity and other wind products also. So my consensus here is, if I'm able to consider similar cases, maybe with that, just with one or two cases, maybe I won't be able to come to a conclusion. Maybe 3 or 4 cases which I'll be doing now. I think then I can kind of conclude with your question, Abhishek.
Okay. Busair, you open your presentation. There actually Mr. Reggie is there. He is actually requesting again.
Thank you.
Yeah. Mr. Reggie, can you please continue?
Is it audible, sir, now?
Okay, madam.
Okay. Thank you, sir. Actually, I had some issues, so I had to come to office right now.
Continue, please. Yeah.
Yeah. Thank you, sir. Thank you for your support. Actually, myself, Reggie Maria. I would like to present a topic that is the meridional gradient of sea surface temperature over the Bay of Bengal and its association with the summer monsoon rainfall in the Indian subcontinent. Well, it is well known that there is a remarkable relation between the SST of the Indian Ocean as well as rainfall. So in this paper, we are going to identify whether there is any potential strength for this SST to identify the active and break period of the Indian summer monsoon over the central India. Can you move to the next slide? Okay. So in this study, we developed a new index, that is Bay of Bengal Meridional SST gradient SST index, which is nothing but the SST different gradient between the equatorial Indian Ocean as well as the North Bay of Bengal. So we identified this SST, and we found there is we could develop an index that is high gradient days and low gradient days. Well, high gradient days are those days when the standard deviation of this SST gradient is greater than 1 in the PSMI, like the the newly developed index, at least for 3 consecutive days, then it is considered as high gradient days. And when the SST index is, or the gradient is less than -1 standard deviation for 3 consecutive days with compared to BSMI, then we consider it a log gradient days. So let's go and deep into why this is important, because based on the high gradient and low gradient days, first we compared the correlation, the spatial correlation between this SST gradient, that is BMSI, as well as the Indian summer monsoon. And we could identify here, there is a high correlation between the BMSI as well as the central Indian, actually all Indian monsoon, but there is a high correlation in the central Indian region, which is above 0.7 and is significant at 95%. And then we checked what is the relation between the rainfall over the central India. So we area averaged the data of the central India and found the correlation between the SST index, that is BMSI, as well as the monsoon. And we could identify there's a proceeding as well as receding phase. Well, proceeding phase is identified in a blue line, and receding phase is identified as red line. Well, in proceeding phase, we could identify there is a correlation of 0.85 with the BSMI as well with and ISMR, and there is a correlation of 0.92 for the receding phase. So these phases are like 30-day phases, no, 60-day phases. Like proceeding phase is 60 days and receding phase is 60 days. So this is actually similar to our BSMI ISO oscillation, that is a 30 to 60-day oscillation, which is driving the Indian summer monsoon. So based on this identification, we could check the composite of monsoon rainfall during the active as well as break period, or the high gradient and low gradient periods. Well, the first plot, that is this one. So this is showing the high gradient period, and this one showing the low gradient period. And in high gradient period, you can see there is a positive rainfall anomaly in the high gradient period, that is central India is showing a positive rainfall anomaly over central India, and there is a negative rainfall anomaly.
Summarize, please. Yeah.
Sir? Okay. And in the low gradient period, there is a negative anomaly in the rainfall. So the rainfall as well as the wind also show the same, the LLJ as well, everything. So we could identify that high gradient and low gradient days are acting just like the active and break days. So we can say with respect to SST index, we can identify active and break period. Then this is a great potential for the further analysis in the future for identifying the active and break.
Thank you.
Thank
Thank you, madam. Thank you. So please,
you, sir.
all others are requested and to visit that main site for the detailed poster. So thank you all presenter. To complete little bit overshoot is there, but out of 22, actually we had actually sir 20 presentations, so only 2 is not there. Otherwise, sir, it is a maximum presentation in this session. So thank you all presenter. So today in the evening there is another session. So all are requested to attend that session in time.
Yeah, that invited session will start at 6 o'clock. That 4 important talks are there, followed by that validity and concluding. So that you must attend. I think. Okay, this same hall will continue. The hall A na, where we are attending this one. The same link will be valid. So you are requested all to join during that time. That is 18 hours, 6. That is 12:30 UTC. Okay. Till that, bye for now. Thank you.
Thank you, sir.